strict time. Then the first talk is by Vadim Kratshov on black hole binaries. So it's 15 minutes, so perhaps I give, after 10 minutes, I give you a sign. So.
Thanks. So I'm glad to be the first speaker of this session, and since most of the talks will be about X-ray binaries or about X-ray polarimetry, so I will try to give you a short introduction to the field so you will understand better all the next talks. And I will start with black holes since I study black hole binaries. So the black hole is a final stage of evolution of the normal star, like massive star. And for most of its lifetime, the star is stable because it's burning hydrogen or helium, producing the heat, which heats up the gas, creating the gas pressure, which balances the gravity. So for most of the lifetime of the star, it is stable. But by the end of the lifetime, the nuclear reactions stop because we are run out of fuel, and we have nothing to balance the gravity anymore. So if the star is massive enough, we have the collapse of the star, and in the supernova explosion, we produce the black hole. And when we want to, if we want to study the black holes, the problem is that they don't produce, by default, by the definition, they don't produce any light by themselves. So it's quite problematic to study the physics of the black holes because we don't see them. So where is the black hole on the night sky? And the answer is that at least 30% of all stars are binary stars. And it means that one star revolves around the other. And at some point of common evolution, we may end up in the situation where one star dies, the way I described just a minute ago. So it collapses to a black hole. And if we are lucky enough, and if the black hole is close enough to the companion star, we may see the transfer of the material from the normal star to a black hole. And this process is called the accretion. And in this process, the matter gets accelerated towards the black hole. And in the process, we have friction in the gas, and it heats up, and it creates the very hot accretion disk around the black hole. And this accretion disk is so hot it reaches millions of kelvins, so it emits X-ray emission. So that's how we see the black holes in binaries, and that's how we can study their physics. But usually, yeah, I'm supposed to have animation here, but we are limited only to PDFs. So the process of accretion looks somehow like that. So we have the transfer of the matter from the star to the black hole, which is somewhere there. And it creates the accretion disk. So everything is very beautiful, and there are a lot of different components there. But in reality, when we observe the objects with our telescopes, we see something more like this. So how can we study the geometry of these systems? How do we know that there are disks? How do we know how they oriented? And for this, we use polarized radiation. It can help us to study the geometry in these systems. So a couple of words about polarization. So polarization of electromagnetic waves, it describes the preferred direction of the electric field oscillations. And if there is no preferred direction of oscillations, we call this light unpolarized. So here we have the combination of all possible polarizations coming from some unpolarized source. And if we pass it through the polarized filter, for example, we will end up having only linearly polarized light, which has some preferred orientation of direction. And we call this light linearly polarized. The good example of unpolarized source is the sun. It produces the unpolarized light because it comes from different parts of the surface of the star, and those parts do not know about each other. So light oscillates in all possible directions. But then if this unpolarized light gets, for example, reflected from the surface, for example, it can be the glass surface or the surface of water or the surface of the road, it gets polarized because in the scattering or in the reflection, the light interacts with electrons in the material, and electrons oscillate more freely parallel to the surface rather than perpendicular to the surface. And one example from the real life is reflection of the sunlight of the glasses or windows. So if we look at the glass in the polarized glasses, and if we orient our head in some particular orientation, we will end up not seeing the glass completely because all the light is linearly polarized, and polarized filter will filter all this light. So we'll end up seeing through the glass. Okay, so this is similar to what happens in cosmic objects in X-ray binaries. We have different components, and we have different sources of reflection and scattering, and in these processes we may end up having polarization, which we can study. And then if we rotate our instrument somehow, we can study the orientation or direction of polarization in these sources. For example, here I show how the companion star's light gets reflected from the accretion disk. And by studying the reflected light, we can study the geometry in these systems. So how do we do that in practice? So in my doctoral research, I used several instruments in optical, and in optical band, where we have this really nice instrument, dipole UF, which was produced in Turku, in Tuorla Observatory by Andrei Berdugan and Vilpu Pirola. And it's installed on Haleakala Observatory at T60 telescope, and it's a visitor instrument on the Nordic Optical Telescope on La Palma. In radio, I used very large array, and in X-rays, the most interesting part, I used recently launched in 2021 XP satellite. It's the first satellite that can measure the polarization of X-rays, and it became possible after like 50 years of research on that because of the creation of gas pixel detectors, which can now be sensitive enough to measure the polarization of the X-rays. So now I will say a couple of words about the black hole the black hole binary I was studying. This is the Cygnus X1, and this is a pretty famous object that was discovered back in the 70s, and it has 40 mass black hole and 20 solar mass companion star. It has the accretion disk, it has the jet, and it is famous for its state transitions. So its X-ray spectrum, it may be soft and it may be hard, and we still don't really understand what is responsible for those states and what causes the transition between the states. And this source was the primary target for the XP mission as a black hole X-ray binary. It was observed as one of the first objects. And before the XP observation, several predictions were made about its possible X-ray polarization. So mostly there were two different theories. One was that the X-ray polarization is coming from the relativistic jet. So this is the accretion disk, this is the relativistic jet. And one theory was that the X-ray polarization is coming from the jet. So in that case, the X-ray polarization was expected to be perpendicular to the jet axis because it's coming from the synchrotron emission. And the other theory was that the X-ray polarization will come from the corona, black hole corona, which is horizontally extended in the plane of the accretion disk. So here I show the image, the radio image of the jet in this Cygnus X1 X-ray binary. So this is just the sky and the radio image. And in 2022, the source was observed with the X-ray polarization, and we found that the X-ray polarization is aligned with the jet, which proves that it's produced in the hot corona above the accretion disk, which is extended horizontally in the plane of the disk. But the problem was that polarization degree, which was observed, was too high. It was more than 4%, and it is too high for the inclination of the source that we have. So my project was to observe the source to understand why we have this high polarization in X-rays. And so we've done in total 13 XP pointings to the source, and we also were observing the source in optical and in radio, and we were able to construct the whole picture of how the polarization in all these bands evolves. So I'll go right to the results. So on the left, you see the X-ray spectra of the source from 2 to 8 keV range, and we covered the hard states where the spectrum is hard, and the soft state as well. So here you can see it from the red to the blue. And what we see that polarization increases as the spectrum hardness. So it goes from 2% in the soft state, where the emission is dominated by the accretion disk, towards about 5% to the hard state, where the emission is dominated by the hot X-ray corona. What we also found is that the angles, the polarization angles in optical, in radio, and in X-rays, they are aligned. They are aligned within a couple of degrees, but they also have some scatter and some variability. So the angle in all the bands, it changes by 5 to 10 degrees, plus minus 5 to 10 degrees. So something causes these variations. And what I was doing, I was trying to explain the variability of the polarization and polarization angle in optical band and in X-ray band. So we see here the Stokes parameters, the parameters of the polarization in optical band and in X-ray band as the function of the orbital phase. So the black hole rotates around the normal star, and it's shown by the orbital phase. So we see that polarization varies with the orbital phase, and to explain it, we need to have a model. So to explain the X-ray polarization, which, by the way, was detected for the first time for the black hole X-ray binary, we ended up having the model in which the inner parts of the accretion disk should be inclined by about 5 degrees, so that we have the precession of these inner parts of the accretion disk as the black hole goes around in the orbit. So this can reproduce the observed shape of the X-ray polarization variability, but of course you can see that the data now is not very precise in the X-rays, so we need more data to create the better orbital profile to be able to distinguish between different models. And one alternative model is that the X-ray emission can come from the shocks in the X-ray binary. So Marpo will be talking about this in this session as well. So what it shows that X-ray polarization can be used to study the geometry in X-ray binaries, and if we combine it with polarization studies in optical band and in radio band, it can put constraints on the accretion mechanisms in X-ray binaries. So in this session, you will hear more about the results from XP. Thank you.
So while we are setting up for the next talk, then quick question, comment.
What are your future plans?
I got the approved new XP proposal to cover 2 more orbits of the source with the X-ray polarization observations, and we are hoping. So this is actually essentially only 1 orbit covered. So if we add more data here, so we will be able to show that either it's a real variability of the source or not, or we will be able to improve the accuracy of the profile, so we will be able to distinguish between different models for these variations. Because for now, any reasonable fitting is not an option, because the error bars are just too large. So we barely have the detection, but maybe in the future we will be able to discuss the physics. And of course, after the launch of the next missions, we will try to put our hands also on the new data from the new missions like EXTP, which will be much better than XP.
Okay, so what about the next talk? Is it remote? Or? So next one is Sofia Forsblom, more XP observations now on Vila X1. Not present, not online. So we move into the next one. So it's then Olavi Kiuru. Yes. So on strong field quantum electrodynamics in magnetar magnetospheres.
Okay, hi everyone. My name is Olavi, and I'm a first-year PhD student from the University of Helsinki in the Computational Astroplasma Physics Research Group. And today I'm going to be talking to you about strong field quantum electrodynamics in magnetar magnetospheres. That's a lot of very technical words, but first I want to give a brief introduction to why I'm doing what I'm doing. So why are we researching this? And the goal is to understand the plasma dynamics of magnetar magnetospheres. And I've put here a plot about the emission spectra of a magnetar as a function of the photon energy. And you can see it has 2 peaks, one here on the left side around 1 kiloelectron volt, and then the other peak is slightly off the plot at around 100 kiloelectron volts. And the first peak here, we suspect it's due to thermal radiation or blackbody radiation, but the other peak, we cannot really explain fully why it is there in the emission spectra. And that is what we want to explain. Probably it's due to some quantum effects, and that's what I'm trying to calculate. So I'm trying to calculate these particle interactions from quantum field theory in the magnetosphere with the special property that we have a very, very strong magnetic field. So here I've defined this Schwinger limit or Schwinger field, which compared to like some of the strongest magnets on Earth, like the LHC particle accelerator, it's 80,000 Gauss. This is 10 to the 13 Gauss, so you have almost 9 orders of magnitude in the difference between the different magnetic fields. So this causes a lot of problems, so we need to use a different type of computational formalism. I will today first give an introduction to magnetars, if they're not familiar to you, some of their basic properties. Then I will talk about how particle dynamics are changed due to a strong magnetic field. And finally, I will talk a bit about cross-sections and what they are and what the cross-sections that I have calculated so far. So magnetars, they are neutron stars. Vadim just talked about black holes. Neutron stars are a bit like a failed black hole. It didn't quite have enough mass to collapse all the way down, but it's still a very compact object. And as the name might suggest, magnetars have large magnetic fields. So they are the neutron stars with the largest magnetic fields, and actually they host the strongest long-lived magnetic fields that we know of currently in the universe. And due to this, they are interesting because they seem to be sources for a lot of these extreme radiative phenomena that we can see from space. Here I put some basic stats about neutron stars and magnetars. So the radius is around 10 kilometers and mass around 1 to 2 solar masses. So you can think very, very compact magnetic fields, so up to 30 Schwinger fields. Magnetars have at least like 100 times stronger magnetic fields compared to other types of neutron stars, and a bit of a slower rotational period compared to other neutron stars due to the strong magnetic field that slows down the rotation. Here's a picture of, or a schematic picture of the magnetic field of the neutron star. There are some properties that I want to highlight. First is the light cylinder. So we assume that the magnetosphere inside, close to the magnetar rotates rigidly together with the star. And if you have a rigidly rotating object, at some point, if you go further and further out from the star, it will start rotating faster than the speed of light, and that's not possible. And that's the light cylinder. It's a theoretical maximum at which you cannot anymore have a rigidly rotating body. And it's also the boundary where we go from closed field lines to open field lines. So the closed field lines start from the surface of the star and end at the surface of the star, whereas the open field lines start from the surface and then go out to the space around the neutron star. These open field lines all originate from the polar caps, so the magnetic poles on the surface of the neutron star, and this is the main area which we are interested in because it seems to be the source of most of the radiation. So what happens at these polar caps is there are electric fields that pull up these charged particles from the surface of the neutron star, and they are accelerated along the magnetic field lines, and they move away from the star. And these field lines are curved, so the charged particles move along curved trajectories and emit photons. And these photons are highly energetic, and due to some quantum mechanical processes, they convert into electron-positron pairs, which then move along curved field lines, emit photons, and create more pairs, and so on. And we get this cascade of particles, and especially we get this cascade of photons in the end that then we can see or observe here on Earth. About the particle dynamics, I have done the approximation that in my work that we, in the magnetar magnetosphere, have just a constant magnetic field and no electric field. And this, for the calculation of particle interactions, this is quite a good approximation for what's happening in the magnetosphere. The main things that keep in mind is that we have charged particles moving in a magnetic field. So what happens is they start to gyrate, and they gyrate along the magnetic field lines on these spiral trajectories. But it's not only the charged particles that are affected by the magnetic field, also the photon polarizations are affected. So we talk about the ordinary and extraordinary modes, and they are defined based on how the polarization vector is directed compared to the external magnetic field. But the thing is, when you really crank up the magnetic field, at some point it's not just enough to say that the charged particles move on these spiral trajectories, but actually these spiral trajectories get quantized. So if you solve the Dirac equation, which is the equation that governs the dynamics of spin half particles like electrons and positrons, you'll find these quantum harmonic oscillator solutions. So the energies are quantized. And really what's quantized is the transverse momenta of the particles. So the momenta that goes around, that's quantized. And you can think of it also in another way as the gyration radii being quantized. So there are only certain radii at which the electrons can gyrate around the magnetic field lines. You can also see this energy gap between different levels is dependent on the magnetic field. So if you have a really strong magnetic field, the gap between different Landau levels, these quantized energy levels, becomes larger and larger. And at some point, no particle can anymore go up to even the first excited level because the energy gap is so large. And then we suddenly have gone from a three-dimensional system into a one-dimensional system because all particles move along the magnetic field line. Shortly about cross-sections. So this is the particle physics part of the talk. Cross-sections are, I think, usually easiest to think about through more classical descriptions. So let's say I have a tennis ball and I'm trying to throw it and hit my backpack on the chair back there. If the backpack is large, it has a large cross-section, then I'm more likely to hit it with the tennis ball. So this is the same for particles. We calculate through quantum field theory, but basically, the larger the cross-section, the more likely it is that particles will collide and actually that something interesting happens. But there's also, we are not only interested in these total cross-sections, we are also interested in differential cross-sections, which give the angular distribution of the outgoing particles. So when I throw this tennis ball and I hit my backpack, we are interested in what angles the tennis ball scatters from the backpack, or the angular distribution after collision. Here I have put a few plots of cross-sections that I've calculated. The one on the left is for Compton scattering. You can see here is the diagram, a Feynman diagram of the process. You have a squiggly line, so a photon coming in, and then an arrow line, so an electron or positron coming in, and then the same particles go out. Whereas on the other side, there's the two photon pair creation, where you have two photons coming in, and then an electron-positron pair going out. And for the Compton scattering, there's a differential cross-section. So this is for a certain angle, and you can see, for example, this dotted line that goes down here. This is the lowest Landau level approximation, where we put everything on the lowest level. So assume everything moves along the magnetic field lines. And you can see it's quite a good approximation for low photon energy. So this is a function of photon energy. But then for larger photon energies, the approximation fails, and we need to take into more things into account. The cross-section has also other interesting features, but I think I'm not going to go too much into detail. You can see there are some resonances and other interesting things. For the two photon pair creation, I have plotted this for different spin states of the electrons and positrons. So you can see that for low energies, there is only one spin combination that we can produce, whereas when you go to higher and higher energies, you get these different spin combinations that we can produce. And also, you can see that the hierarchy between the different spin combinations changes depending on the photon energies. So if you have a certain energy, you are more likely to produce certain spin states compared to others. Well, what's about the future? What am I going to do now that I've calculated? So I've calculated these are some of the processes that you can calculate. I've calculated all the way down to Compton scattering. There are still some other processes that can be calculated. So still a lot to do. And also there are other open questions, like what about the electric field? Because I set it to 0, but maybe that's not a good approximation. We don't know. The math seems to get even more messy and complicated, but it seems maybe doable, so it's something I want to look into at some point. Also, what I'm really, the plan for the rest of this year, at least for me, is to start doing these plasma simulations of magnetar magnetospheres. And see, especially these processes that have these gamma, so the photons, those are interesting because we really want to explain this emission spectra. And we want to explain the high energy peak of the emission spectra. And to do this, we need to know which of these processes are important in the dynamics, and especially the photons, because the photons are what we see, so we want to focus on those processes. So to give a brief summary, we are interested in explaining this emission spectra, but to do this, we need to understand how quantum electrodynamics is modified due to a strong magnetic field, and we need to calculate all of these cross-sections that govern the plasma dynamics of magnetar magnetospheres. And really, the one thing that is key for all of this are these Landau levels. they govern everything that happens in this strong magnetic field. So if you understand the lambda levels of the electrons and positrons, then that's the first and key step to understanding the full plasma dynamics. Thank you for me. If you have any questions, I'd be happy to answer.
Do you preserve the information about the polarization of photons in your treatment? So will you be able to explain maybe polarization results on magnetars in like X-rays? Yeah.
If not, then let's thank Olavi again. And the next one is Anna Bobrikova, more on the polarization of neutron stars.
Really close, like this. I'll try, but I cannot promise anything, people. Hi, I'm Anna. I'm from the University of Turku, and today I'm going to talk to you a little bit about what are the weakly magnetized neutron stars, what are their parts of their emission, and how do you increase the polarization of their emission by tilting them and breaking the symmetry. So I'm going to be standing quite heavily on the foundation that Vadim and Olavi have established now. So I'm just going to start with the X-ray binary. And we're going to see at what do we actually have. From far away, they all look the same. There is a donor star, there is some disk, and then something is happening here. And it strongly depends on the compact object, and it's something that we are trying to establish now. So Vadim talked about what happens if it's a black hole. Already established that what's going to happen if there is a strong magnetic field. But what if the star didn't only fail to become a black hole, it also failed to produce a strong magnetic field? Well, then we're going to get the brightest objects on the X-ray sky. So we're going to have some sort of, innermost stable boundary of the disk on one side, and we're going to have the strong surface of the neutron star on the other, and something that happens in between is a mess. And that's what we're going to try to study. And that's what we're going to try to analyze. And because we're looking into geometry, of course, we need polarimetry. So let's establish some terminology. So we do have the disk, and we're going to call it a disk. We have the neutron star surface, and between the disk and the surface, there is some boundary layer. And if the matter is not only stuck between the neutron star and the disk, it also spreads onto the surface of the neutron star, we call it a spreading layer. So far, makes sense. Then we're going to also add some wind, and we're going to add some reflection of the emission of the spreading layer from the disk, and that's basically all we have. So these guys, the boundary, the spreading, and the disk, they make the continuum, and the wind and the reflection are just some sparkles on top of the continuum, as you can see here. This is the typical spectrum of the sources. So we do have the disk making a major contribution, the harder component making an even larger contribution at higher energies. And we do have these little addings of the wind and of the reflection from the disk. So this is spectroscopy, right? And now we need to think about how can it look like in polarimetry? What is the polarized emission of each of these components? And this is a dense slide, but the idea is that for every bit of this, for every component, there has been some theoretical research that gave some predictions on what can we actually expect from every part of the emission. And what I want to remember is in the disk, we expect something about 2% for most of the stars. It kind of gets to 6 with very, very high inclination, but we're not going to go there. Most of the stars don't have it. So with the spreading layer, I'm going to talk about it right now. With the boundary layer, our assumption here is that it's a disk, but hotter. And then we have some higher expectations for the sparkles, but they have minor contribution to the spectrum. So overall, so far, we're trying to build our expectations for the continuum. So I'm going to talk about the spreading layer, and I'm going to tell you how we build it in our model. It's pretty straightforward. This is a first approximation. So we do have a very basic situation. So there is a horizontal disk somewhere. There is a spreading layer between the two lines on the surface. They can be anywhere, doesn't really matter. We have an observer somewhere here. And then we put some black hole, some black body emission on the spreading layer. And we're going to add some uniformal rotation of the matter, and we're going to add some basic assumption for a polarization of the endlessly thick uniformal, isothermal, whatever basic slab, which is from the 60s. So that's the basic assumption, and it's just going to quickly look at the results. A lot of lines are here only to tell you that we have tested a lot of geometries, we have tested a lot of different combinations of the parameters. For all of them, the result is that we have very low polarization degree, less than 1%, and that we have the polarization angle, which is almost always at 0 or somewhere around it, which is orthogonal to the disk plane. That's the conclusion I want you to remember. Okay, let's make it a little bit more physical. So we're going to think, okay, imagine this flow. Imagine the matter coming from the accretion disk to the neutron star surface. Of course, it's not uniformly. It's not isothermal. It's going to be rotating at different speeds. It's going to be like levitating at Keplerians on the equator. It's going to be slowing down on the edge of the spreading layer. So let's try to introduce that. Let's try to introduce some dependency of the temperature, some dependency of the velocity, and also thickness. It cannot be infinitely thick. Let's think about it. So we added a lot of physics into the process. The results did not change at all. We did have a little bit more quirky, but still very low polarization degree, and a little bit more like shifting, but mostly still polarization angle in orthogonal to the disk plane. And then we look at the results, of course, because we have a lot of XP observations of these sources. As I told you, these are the brightest objects on the X-ray sky, except for the sun. So we have maybe 20 observations of these. And we're like, do these expectations that are like align with the results? And the answer is not really. They don't. So for instance, this is one of the examples, one of the brightest sources on the sky. And you can see that these here we can see almost a 6% polarization from the harder component, and they're also not orthogonally polarized. So there are some questions. And then, on top of all these questions, we have Surson 61. Surson 61 is the youngest neutron star known to humanity. It's very young, it's crooked, it has extreme eccentricity, and we are almost sure that it's tilted. That was our only assumption, because we looked at the results, and the results says that the polarization angle in this source doesn't only change with energy, it also changes with time and with hardness and with basically anything. So something really crazy is happening in this source, and we looked at it and we tried to come up with any sensible conclusion, but the only idea we got, which it might actually work, is that we tilted this neutron star. Which is not something you normally do, but in this situation we didn't have any other choice. And then we decided it might work, as was explained in John's paper, and then we also had to calculate it. So we tilted the neutron star. And yeah, and so because of that, you add 2 more parameters to your system, but otherwise the model is pretty much the same, right? Now we have the angle of the misalignment, and then we also have the azimuthal angle, because it becomes suddenly important from which place on this, like you're looking from here or from here. So we have 2 more parameters. Otherwise, the system is pretty much the same, and I'm just going to jump to results. So here we can see that the polarization degree instantly rises a little bit for some of the, I'm not going to go through which parameter is which, but for some of the combination of parameters, for some of the systems, it rises. And also the polarization angle now is just all over the place. So technically that's what we wanted, because that's something we have in the observational results. And of course, I'm going to only show you one picture. So we went further and we investigated the parameter space. because like we wanted to see polarization degree and polarization angle as functions of these new parameters of the misalignment angle and of the azimuthal angle. And you can see that for like if you tune your parameter space, then you can have pretty high polarization, which is something that we see in the data. And you can, in theory, get any level, any polarization angle you want. So that's some hope. And my conclusions are pretty simple. If you really want to improve and increase your polarization angle, breaking the symmetry helps. Well, this kind of expected. We found a place in the misalignment parameter space where PD gets high error, at least not high enough that we need, but at least it's getting higher. And the question is, does it mean that all the objects that we have seen with the polarization degree expecting 2% are observed from these angles and are misaligned? Of course not, but some of them might. And we're working now on predictions for the upcoming observations of on these objects. And please stay tuned to see if we got at least some of these myths right. Thank you for your attention.
Thanks for the presentation. It was interesting. I have a question related to the previous slide. So we have the polarization degree and position angle maps. So there is this inclination of 70 degrees, but so where is the core here exactly, or of the object? Or can you a bit elaborate what we are actually seeing here? Like which region is this? Like, do we also see the background? Oh, okay. Sorry.
This is a million of different systems. Imagining that we are observing the system from this angle on the azimuthal plane, and it can be tilted like this. So each point on this plot is a system. And yeah, the only thing we can conclude from this plot actually is that if we're observing the source like from these angles azimuthally, and if it's tilted by 15 to 45 degrees, like these just misaligned like this, then we get high polarization. And if you, like, depending on what polarization angle you actually want, you can also kind of have a hint of, like, if you look at the XP observations and you see what you actually got, then you can see if there is some sort of parameter space on these angles that fit both your polarization degree and polarization angle predictions, which, spoiler alert, doesn't normally happen. But we're working on it. Thank you.
Thanks. So we move on to the final talk in the session, Varpu Alberg from Turku. So on super Eddington accretion.
All right. Good morning, everyone. I'm Varpu, also from the University of Turku. I'm going to continue on a similar kind of topic, but different from what Adi mentioned, sadly, but you can ask about that later. So it's about the polarized signatures of super Eddington accretion. So what does this mean? Oh, wrong direction. Whatever. So, as a recap, accretion is an extremely efficient way of transforming gravitational energy to light. And in fact, it's more efficient than stars are at making light. So in the right here, we have an illustration of an X-ray binary. So we have a regular star, which is donating mass to either a black hole or a neutron star. And as the mass is spiraling in towards this compact object, it gets so hot, it starts to emit X-ray light. And some of the brightest objects in the universe are accreting compact objects like this. But there is a limit to their brightness. This is called the Eddington limit. If something gets extremely bright, the pressure of the light pushing outwards can get more powerful than gravity. So basically what happens, it can no longer stay together and blows up. So in the context of X-ray binaries, the brightness of the accretion disk depends on the amount of mass it is being fed. So if you have an X-ray binary that is receiving a lot of mass, then it could theoretically go over the Eddington limit. So what happens then is the excess mass that is being fed to it is going to be blown out in this huge wind from the inner accretion disk. Because otherwise, well, it would go over the Eddington limit, and that's not really possible. So this should be like a upper limit to the brightness of X-ray binaries, but nature has its ways of throwing curveballs at us. Oh, ultraluminous X-ray sources, also known as ULXs. So we see these objects in other galaxies. They are point-like objects we see in the disks of the galaxies, so not at the center, they're not supermassive black holes. And they seem to exceed the Eddington limit for solar mass objects. And this, like on a naive level, shouldn't be possible, because if it was that bright, then it shouldn't be able to accrete more and get brighter. So what's going on? So there's some ideas for this. One possibility is that they're heavier than solar mass objects, so they have stronger gravity, and so it's can get brighter. The Eddington limit is higher. So it could be an intermediate mass black hole. So instead of like 10 solar masses, it could be 100. But the issue is with this idea is we really don't know how we even make intermediate mass black holes or how they end up in X-ray binaries. And we see so many ULXs, it's not really likely that all of them are intermediate mass black holes. Then maybe there's some physical process that allows the Eddington limit to be surpassed. One idea for this is, for example, this photon bubble instability, which basically allows the light to leave the system without too much interacting with the gas, and you could get more luminosity than the Eddington limit. But this has the issue that it can only really explain something being like a few times brighter than the Eddington limit. And some ULXs are like 100 times brighter, so there has to be some other consistent explanation. And the best we have right now is beaming. What does this mean? So, as I mentioned, in a super Eddington accreting source, the excess mass that would take it over the Eddington limit is going to be ejected. And it's going to create this sort of big outflow surrounding the source, and it sort of creates this shell around it that we cannot see through. And the light can only escape from this sort of narrow angle in this funnel. So it kind of acts like a mirror. It focuses all of the light into this narrow beam, and by doing so, if we are looking right down this funnel, it appears much brighter than the Eddington luminosity, even though it isn't. So we see these things in other galaxies, but what about the Milky Way? So there is evidence that some X-ray binaries in our galaxy are in fact ULXs, but just pointed away from us. Most famous example would be SS433, a very long-studied object. I think Carl Sagan called it one of the wonders of the universe, something like that. One of the interesting things about these sort of obscure ULXs is that you wouldn't be able to see them directly from like the central radiation coming from the accretion disk. Instead, you would see the reflection of that light from the inner surface of this funnel. And as Vanim explained, when you have scattering or reflection, you polarize light. And if we see nothing but scattered light, it should be very strongly polarized. Well, in recent years, IXPE has observed this X-ray binary called Cygnus X3 and found it has a very strong polarization degree. This was found consistent theoretically with this sort of obscuring outflow surrounding it. So it's maybe another obscure DLX. But one strange thing about Cygnus X3 specifically is that the polarization changes with its spectrum. So normally it's around 20%, but sometimes the spectrum gets softer and the polarization degree tops to like 10%, which is still large. It still appears to be a obscured source, but it still drops by half. So one idea is there's some change in the flow. Maybe there's gas forming on top of the funnel and we're seeing light scattered from that, or like inside the funnel, something like that. And that is something we wanted to test. So previously this sort of thing has been modeled analytically, but it doesn't take into account multiple scatterings or reflections between these funnel walls. So what we wanted to do is start with this like simplified Monte Carlo simulation of how light bounces around these walls and see what sort of polarization we get. We explored some parameter space here. So first off, different amounts of reflection versus absorption in the funnel, and different shapes of the funnels or different opening angles and such. And we also added the option of like filling the inside of the funnel with some gas or adding some gas on top of the funnel. So some results here. On the image on the right, you see on top the reflected polarization degree and the flux as a function of the inclination or viewing angle, 0 degrees, meaning we are looking right down the funnel. And here the different colors mean different ratios between the scattering and the absorption cross sections. Blue here being the most absorbed one, and the magenta being just nothing but scattering. And an interesting thing we found here is that this scattering doesn't really produce this beaming unless there's basically no absorption present. But if there is no absorption present, there's so many scatterings that the polarization degree plummets. It's below 5%, which is not something we see in Cygnus X3. So this has some implications. Since we see a strong polarization from Cygnus X3, and if it is beamed, then there has to be a more complex structure to this funnel outflow, or this like different layers of ionization, different amounts of scattering and absorption in different levels, or re-emission of the absorbed emission instead of just scattering should play some sort of role in the beaming. Then for like adding gas on top of this funnel. So this is sort of an illustration of that idea. This different spectral states of Cygnus X3, and in this hard state, which it most usually is in, we think we only see like the reflection from the surface of this funnel. But as we go into these softer spectral states, there's some sort of gas piling on top of the funnel, and we see scattering off of that, and it changes the polarization. And here's sort of a figure of that. It's using optical depth as a parameter, basically like opacity, like how much gas is there on top of the funnel. And as we increase the optical depth, this is around the viewing angle we expect from Cygnus X3, the polarization degree starts tending towards the 10% value that we actually see. There's some nuance to this, but I don't have time to really get into it here. But it does seem that this can kind of explain the changes in polarization in Cygnus X3. So, some conclusions. ULXs, they represent a different mode of accretion than most X-ray binaries, and it's not perfectly understood. They are rather hard to study because they are very distant objects, but luckily we have these potentially obscure DLXs in the Milky Way that we can observe. And with the polarized signal we get from them, it can help us understand the structure of their outflows. The high degree of polarization in Cygnus X3 indicates that there is significant absorption present. And this means that it cannot be beamed simply via reflection alone. So it seems to be a more complex process, and this is something we are going to work, like, gonna expand our code next to try different versions of that. Then, yeah, buildup of gas inside or above the funnel can reduce the polarization. And yeah, this seems to be consistent with what we see in Cygnus X3. Thank you. Yeah, so going into here, so when the luminosity at the inner accretion disk goes towards the Eddington limit, the radiation pressure gets high enough that it starts blowing out the surface layers of the disk in a strong wind. And it goes in this sort of geometry where it like leaves a cavity at the center, but like you get this sort of shell surrounding it. Yeah, it's somewhere. Specifically with Cygnus X3, something we thought about is that, so it is a wind accreting source. So it is probably a black hole orbiting around a Wolf-Rayet star. It has very strong wind. And so there should be just a lot of gas around. So you could get, like, I would assume the radiation could like clear away some of that gas, but who knows, maybe there's like increased amounts of gas going over at some point.
And if this Sophia Forsblom has not appeared, then this closes this part of the session. So the next item is coffee break. And then we should reconvene 10:45. So thanks. Yeah, let's thank all the speakers.
Hello, this is room audio test. The microphone is plugged in. I'm currently standing in front of the room. Check the audio. So if I speak like this, does this sound alright? Let's see. Can you hear me? Someone? Can you hear the audience? Someone? Should I increase the gain?
1, 2, 3, yes, working. Okay, so welcome to the second half of the astronomy session. So I don't know if I'm chairing also this one. I'm also talking, so I try to keep time. But so my topic is galactic astronomy, observations of interstellar medium and star formation using some satellite observations. And the target is Orion molecular cloud.
If you click the screen once, it might work.
Okay. Yes, it is one of the most famous molecular clouds, Orion, and so yes. So the background is the star formation. So we are looking at the interstellar medium and clouds in the interstellar space and how they are collapsing to form stars. And now one thing to remember is the categorization of structures of these interstellar clouds. You can have clouds at large scales, you have clumps, then you have cores which are collapsing. They can be prestellar or protostellar if you have already a protostar forming inside the cloud. And then the end result is a planetary system and some kind of star. But also, especially then in the recent years, one has recognized that this is not a quite accurate picture. You have also very elongated structures, filaments in the molecular clouds, and then even at the later stages of the star formation, you have streamers, narrow filaments of gas and dust which are falling into the forming star. So this is an all-skies image of the Milky Way, so at 350 microns, and you can see the galactic plane, and then everything you see here is just thermal emission from dust grains within the interstellar clouds. So it's interesting that within these gas clouds you have also solid particles, dust particles, which are affecting the physics of the medium, but also, as in this picture, are useful in tracing the structures in the Milky Way. So you can pick any of the nearby clouds and study them in more detail, but today let's look at this region. So there you have actually the Orion region and Orion A and B clouds, which are Orion A is the nearest region to us, where you have actually formation of massive stars, so more than 8 solar masses. So if we turn this from galactic projection to equatorial coordinates, then you can make here the comparison to optical observations. So the Orion belt is here, and the Orion Nebula is here. And also there is a prominent Lambda Orionis region, old supernova remnant in the northern part. So we have been looking at this region or different parts of this region. So Emma Manfors has been now looking at, for example, the Orion, Lambda Orionis region. We have now observations of a very small, extremely dense prestellar core with ALMA. We have been looking at some of the reflection nebulae, even the Witchhead Nebula there, and then especially many papers on this small cloud, which is the LINS 1642, with just a few low mass stars forming. But now, in the recent years, we have been concentrating more on this OMC3. So it's Orion Molecular Cloud 3, part of this Orion A cloud. And now I'm talking part of this project, looking at some infrared radio observations. So if you zoom into this region, then actually you see there's a prominent filament, which is the so-called integral-shaped filament. And here are some this is collage or combination of observations of different wavelengths. Here, this orange color corresponds to line emissions or ammonia spectral line observations. Here you have the same part. So this is actually the OMC3 region where you have this kind of Y-shaped filament. And this is kind of interesting paper because there one made observations at millimeter continuum. and even longer wavelengths, and one was looking at the spectrum and interpreted that at some point as an indication of very large dust grains. So in the interstellar space, the dust grains are less than 0.1 micrometer in size, but during the star formation process, the grains are growing, and then the question is, how large are the grains where you have when you reach this protostellar stage? Because it affects the physics of the accretion disks, etc. Now, if we are looking at just this one question, what are the dust properties in the Orion, we can make use, for example, first of the Herschel far-infrared observations of the dust continuum and combine that with near-infrared extinction observations, which are based on the reddening of background stars. So we have near-infrared, a few micron, and then hundreds of micron far-infrared extinction combined with the emission. And the idea is that we have done just modeling, try different properties of the dust, and also very different other basic ingredients of these models. So there's the cloud structure, radiation field, etc. And when you test these different properties, use different assumptions of the dust grains, grain sizes, etc., you can fit the observations. So here are Herschel observations, some model, and usually you get pretty good match to the observations with almost any dust properties, but there are significant changes, for example, at the near-infrared range. If you assume that the grains are very large, then your extinction curve turns flat, and then because the extinction at near-infrared wavelengths is based on the color of the radiation, if your extinction curve is flat, then there should not be any correlation between the colors and the extinction. So at some point, these kind of models are excluded just because they would not produce any color signature. Also, otherwise, if you are varying the size of the grains, you are changing not only the near-infrared extinction curve, but also for the long wavelengths where you have the Rayleigh-Jeans tail of the emission, which is now being probed by Herschel, the slope of that is affected by the grain size. So again, at some point, if you assume very large grains, then this beta parameter, so the opacity spectral index gets too large. So it gets very steep at those long wavelengths. So after testing hundreds of models, then one can get some general conclusions so that the far infrared part is fitted best with many dust models, aggregates, and with or without ice mantles, but grain sizes are limited to at most 0.3 microns. So compared to some of these earlier claims, which were already kind of corrected at some point, this is very far from the kind of most radical suggestions of millimeter-sized grains in the general Orion region. Also then, independently of this, you can look at also at the kind of the structure you see in the far infrared, and then the extinction you see in near infrared. So what is seen here is that you have these very high column density regions which are not visible in the extinction map. So one interpretation for that could be that perhaps in part, so in this ridge where you have the highest densities, highest column densities, perhaps there are some very large dust grains which would explain the lack of correlation, so that the colors no longer are tracing those high column densities. On the other hand, because of the high column densities, there's also very few background stars visible, so the evidence here is not very strong. So this was actually the second part already of the study of the Orion. The first was looking at the structure of the filament using far infrared emission and also mid-infrared absorption. Now, in this study, we looked only at the kind of large grains and far infrared emission combined with near infrared extinction. But now the next step is to combine or add also longer wavelengths, Planck observations up to centimeter wavelengths, and then include also shorter wavelengths. So in these spectra, here are Planck points. This is the Herschel observations. But then on this side, you have also the observations of stochastically heated small grains, which is kind of traced by Spitzer observations at this point, Spitzer and Weiss satellite observations. So you have complete spectrum, and now it's a bit more complicated modeling because of this separate physics of the large grains, which are kind of at an equilibrium temperature, and then what you see at mid-infrared wavelengths, where you see mainly just the stochastically heated grains, so they are fluctuating in temperature, and therefore the modeling of that emission is a bit more complicated. But the kind of preliminary result from this is that if you just look at this spectral index now combining Herschel and Planck, and you have to make some corrections for CO emission because you have line contamination in the Planck bands, then you can recover more or less kind of normal spectral index. So again, this Rayleigh-Jeans tail of the opacity spectrum, and this doesn't require any exceptionally large grains. But as said, the next step is to characterize the abundance and the properties of the small grains. Okay, so that's more or less my talk today. So this Orion OMC3 is not exceptional. We have looked at many lower mass star-forming regions, and the results have been very similar. Spectral index are below 2, and there's no need to assume any number of very large dust grains, such as larger than 10 microns. Actually, those are excluded. And the combination of far-infrared emission and near-infrared extinction is very powerful in excluding many of the dust models. Because dust models tend to have a kind of not large enough difference between the near-infrared opacity and the far-infrared opacity. So you need a dust model where you have this larger difference between near-infrared and far-infrared, and that usually means some kind of aggregates or larger grains, but not very large grains. Okay, so actually then perhaps when we have a model to these, then at some point we also can include then James Webb observations. They are starting probably next month, but the goal here is not to look at the dust properties so much as the very smallest scales of the structure. So the structure of the filaments cores, and then look at the streamers and perhaps also even down to disks. So these streamers are very interesting because it seems that even at later stages, when you have already, perhaps you are forming planets, then you can still have streamers which are imparting angular momentum to the disk, and changing the disk properties may then even affect the formation of planets. But that's my talk today, so thank you. Questions?
Can your modeling judge spatial variations in the dust?
Yeah, so in this study, it was mainly just two components. So assume that you have some dust properties in the extended filament, and then you can assume that at some point at above some density threshold, you are moving to even larger grains. So that kind of things we experimented. For example, in this picture, there is always two dust components, one for the extended region and one for the central region. But I would say that these kind of observations have very weak constraints on this kind of dust evolution within the filament. So. Okay, let's thank me. And next talk is by Mikael Turkki on AGN.
Do I have the remote somewhere? Or is it? Oh. Hello, my name is Mikael Turkki and I'm a first year doctoral student at University of Turku, and today I'm going to talk about magnetic field structure of actic-anactic nucleus in 3C120 and the ALMA polarization observations. As this is not a extragalactic jet conference, I'm going to briefly talk about 3 questions that are open, but I consider central in this slide. So, first of all, what are we even talking about? So, the extragalactic jets, here on the image on the right, you can see these extended structures in radio frequencies, which are coming out of this galaxy, which has a supermassive black hole in the center. So not all active galactic nuclei have these jets that we observe in radio. In fact, it's like about 10 to 20% of them. But at the moment, we don't actually know why this is the case, that like why some systems have jets and why some do not. And another point is that we know that these plasma jets are visible across the electromagnetic spectrum, but we don't really know if they consist of electrons or protons, of a combination of these two. So there are other experts in Finland who know more about this topic, and their talks will be presented in the Nordic Baltic Astronomers Day in May. And then the third point, what I've emphasized here, is what interests me personally. That is what is the mechanism that initiates the jet launch, and which part of the black hole environment is responsible for the energy we see in these jets. So, two most prominent theories are that the energy that fuels these jets come from the rotational energy of the supermassive black hole, or alternatively the accretion disk surrounding it. But in both of these cases, what is relevant is the role of the magnetic fields, which I'm interested in studying. So here in the figure on the right, I have illustrated this or demonstrated this like helical magnetic field structure that is happening in the near vicinity of the supermassive black hole there. So there is this acceleration and collimation zone, after which the jet becomes like more or less pointed at either direction. So, and to study this region, we have to get quite close to the jet base, meaning that we have to have very high resolution. And also we need to perform the observations at high frequencies, so that the region we are looking at is optically thin. And here I'm just, to give you some context, I'm talking about frequencies over 100 gigahertz or wavelengths smaller than 3 millimeters. And as we are interested in magnetic fields, we can get this quantity Faraday rotation measure from polarimetric observations, which is physically based on the electron density and the magnetic field strength at the area we are looking at. And this Faraday rotation occurs if and where the photons encounter a magnetized medium, meaning that the emission gets depolarized. So this quantity we get from linear polarization observations when we look at the electric vector position angle and its variation as a function of frequency, or here wavelength square. So here on the right, there is a radio image of the source that is under investigation, 3C120, that in earlier work it has been observed in lower frequencies, and closer to the jet base at the region A, we can see this rotation measure gradient that is clearly non-zero, whereas in this B region it is flat, meaning that if there is like magnetic field structure, it must be stronger in the region A, and in region B the magnetic field or electron density is very, very low. So in my work, the data I have analyzed comes from ALMA in Chile. So we get full polarization data based on these antennae, and we obtain data at two different bands, the 2 mm band and 1.3 mm band. And here you can see 4 data points in these plots A and B, which correspond to spectral windows. But in these data, you can also separate them in channels and get like more data points, but the idea is similar. So here are the results based on the analysis. So what we see in both bands is basically a high rotation measure, meaning that there must be either a dense, like the electron density must be high or a high magnetic field. So, and we are expecting to have this linear trend as the rotation measure is basically like how it should behave would be linear, but in band 4 in the left panel we actually see some possibly sinusoidal movement, and I'm interested to find out what this physically means. So at the moment, at least I don't know. So one thing I want to point out here is that these observations 8 months apart, so they have to be treated as 2 different data sets. So in this study where we want to point out the depolarization mechanism we see in 3C120, from the models we compared, we were unable to rule out, point out the single one, but we were able to rule out some scenarios. For example, in this model, what is depicted here is that there is at some distance of the jet, there is some sort of Faraday screen that should depolarize emission as a function of wavelength, but this obviously, as you can see, cannot happen based on these observations. And then conclusions and future work. So the number of components responsible for the depolarization near the jet base is still open, but we can rule out a distant Faraday screen, which is illustrated here on the right. But yeah, so either we need more ALMA data or event horizon telescope time to resolve the system. And here, why the ALMA and event horizon telescope have been included there is that it's illustrated that ALMA, if there is such structures that 1 or 2 screens or multiple components, ALMA may not be able to resolve them. But with event horizon telescope, you could actually get observe only the compact structures there. And in addition to 3C120, we also have data from 2 other targets, which analysis is currently in progress. And there is also more already existing observations in the ALMA archive to conduct variability studies. Time variability studies, I mean. So thank you, and I'm happy to answer any questions.
Okay, plenty of time for questions. Please go ahead.
Thank you for the very nice talk. Polarization with ALMA is really tough. So even though you showed like this linear fit, I know it's a lot of work to get those data well calibrated. What about internal variability in the AGN? So not a screen, just kind of variability because AGNs are complicated. Have you considered that in those 7 months?
Yes. The fact that they cannot be treated as a unified set is that there is time variability, and there was actually a flare in between these two epochs, which ideally they should be taken as close together as possible, but this is what we have to work with.
Thank you. It's very nice work.
So more questions? So again, what was the resolution with ALMA? So can you still improve with going to other configurations or higher frequencies?
So basically the resolution can be best improved with having like multiple telescopes works as an interferometer. I would say that is the way to go and improve, either with Event Horizon Telescope or Global Millimeter VLBI Array, GMVA.
Okay. So if no other questions, then let's thank Mikael again. And the next one is Job Forster, Young Stellar Objects and the Metsähovi Compact Array.
This is easier. Thank you. Hi everyone, I'm Job. I'm going to talk about some work we've been doing at the Metsähovi Radio Observatory. I'm just a science guy, so I've been writing literature reviews and helping the instrument team where they should point. But most of the work was done by Derek, Jere, Damien, and Sonny. We've been having regular meetings. So let me tell about our project to search for accretion bursts from high-mass young stellar objects with a Metsähovi compact array. So, basic introduction, stars form disks around them and jets, which are very important. The physics of these disks and jets affects both the large-scale evolution of clouds that Mika spoke about earlier, but also these disks are where planets form. So the physics of protostellar disks are very complicated. For example, the fact is that these disks, especially in high-mass young stellar objects, are so massive that they form these clumps inside. They become gravitationally unstable. There's also some magnetohydrodynamic effects that can also cause these clumping. Here is, for example, a simulation which shows the formation of these clumps, and as they migrate inward due to disk viscosity, they can fall onto the star and release a lot of gravitational potential energy. Here the bottom plot shows the leftmost one is the growth of the stellar mass. They have these small jumps. The middle plot is the protostellar luminosity, its light output. Now, what you can see is that this is not smooth, it's very spiky. So the simulations suggest that high-mass young stellar objects gain about half of their mass in about 3% of their formation time. That this burst mode of accretion is kind of very important for their mass growth. So stars don't grow, and this is seen throughout the stellar mass range, but stars don't grow continuously when they're young, but they grow with these bursts, every time releasing a lot of energy. And this is the accretion rate of the stars. And as more work has been done on these accretion bursts, there's been actually found that they have a lot of different effects on the physics. They're kind of complicated. They can heat the surrounding environment, melting ice of dust grains, affecting those, so those ice molecules go into the gas phase, that affects the chemistry. They can also change the dust properties by melting the dust, changing them from amorphous grains to crystalline. This is kind of consistent with what we find in asteroids. These accretion bursts eject gas into the surrounding environment. They kind of make these clumps in the jets. And they can even eject dust grains, which is kind of very new field of study, like how these accretion bursts can cause dust to be thrown up into the envelopes. And they might help or hinder planet formation, but the jury is completely open about the effect of this episodic accretion on planet formation. So this is just two results. For example, this is a dust changed from amorphous, where it has this smooth shape, to crystalline, where it has more defined features. And this is just a little image to show as you add a lot of heat to your environment, you melt the ice off, and you also change the dust properties. But there's only been about 10 high mass accretion bursts detected since the first one, which was detected in 2017. They are quite hard to find because high mass stars are rare, they're deeply embedded. Yeah. Now, one tracer that has been relatively successful in finding these accretion bursts is astrophysical masers. Now, you know how if you drive behind another car, smoke blocks light? So that's called opacity, blocking light. A maser is when your opacity is negative. And so it's a cloud that amplifies background radiation. The physics of it is quantum. You have population inversion. You have more particles in an upper energy level than a lower energy level. Then you get through stimulated emission. You can have exponential amplification along the path length. So masers look like very bright point-like sources, which is very nice. They're very sensitive to physical conditions. So they're kind of like a easy observable for very small-scale physical changes, such as accretion bursts. This single-dish maser monitoring has been done for about 20 years. The specific maser we're looking at, 6.7 gigahertz methanol masers, was discovered in the 1990s, and the first accretion burst was detected in 2015. So this is an example of how the observations would look. You have a spectra, they have different velocity components corresponding to different blue shift and red shift, and then you can make a time series from these spectra. And then if you find a burst, you can tell the international facilities, very long baseline interferometry, ALMA, James Webb, VLA, and you can take a lot of pictures. Because these bursts they happen in less than a year's time. So you need very quick kind of notification, and then boom, 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 you observe it with all kind of instruments. One example that was quite dramatic, in this G358, there was a 6.7 gigahertz methanol maser flare. These particular masers are only associated with high mass star forming regions, so they're a great tracer. And radiative transfer simulations have shown that they follow the infrared radiation very well that is associated with these bursts. So there was a flare. You can see here the red was 2 February 2019, and the blue was 3 weeks later. The components flared by a factor of 7, some of them. And this was observed with ALMA, VLBI, and they found it's consistent with an explosion traveling at 4% the speed of light. So when you had this accretion burst, there was a heat wave that traveled at 4% the speed of light, melting ice off of dust grains and making these masers flare. So this is a ALMA observation, quite recent work, 2025. This was also done with very long baseline interferometry, and you can see here the maser spots. This is day 20, day 50, day 60. You can see they're moving outward as the heat wave is propagating. They are very exciting science targets, but even though about 10 monitoring stations worldwide have been trying to find them, only no accretion bursts have been detected in real time in the last 5 years. So there was a lot of detections and then not so many. And so we have a new kind of observational strategy to find these accretion bursts. And this is small dish interferometric monitoring. Because small dishes have very large beams. But if you make it an interferometer, you can actually cover multiple star-forming regions at the same time. So you can kind of cover like 5 or 6 or 7 simultaneously. That is my phone. I apologize. Seems like I have a talk. Okay. So we have, at the Metsa-Hovi compact array, we have an array of small dishes And we are building towards an interferometer so that we can monitor multiple star-forming regions simultaneously. So these are our instruments. You can see here's the big Metsähovi radio observatory dish. And these 3 antennae are the Metsähovi compact array 5-meter dishes. MCA1 and MCA2, those 2 work already. They are operational. MCA3 just had first light very recently. They are 5.5-meter dishes. They're very fast, so they can do quick integrations. We have C-band, so 4 to 8 gigahertz spectral line observations. And interferometric mode is already working, starting to work. So this is our workflow. We have to make a few changes because we have very small dishes that are not sensitive. You have to be smart with how you do your data reduction. So first, with regards to scheduling, we've been doing 500 hours of observations per month with about 60 maser sources. For context, like the big single dishes also do around 70. So we're competing with the international facilities in terms of coverage. But because we have small dishes, we actually cover hundreds of star-forming regions within our beams with our monitoring. We have automated observing, so it's not a lot of work after you do the automation, which allows us time to do other things. And so we integrate over our whole source list every day for 10 minutes, even though we might or might not detect a particular maser. Some things on the calibration. One of the students has developed a median calibration where we have our spectrum, we cut it, but we move the center frequency of our observations, and that allows us to get an estimate of our band pass automatically to get flat maser spectra. And we also, flux calibration is still in progress. To get our flux calibration working, we took masers that we've been monitoring for about a year and took literature flux values for them to kind of get an estimate how to get to Janskis. This is probably the biggest source of uncertainty for our observations at the moment. This is in progress. So we've observed around 60 sources, and you can see with these average spectra that we've detected quite a lot of masers. We have a single integration sensitivity of around 100 Janskis, but if you average them, we can go down to 10 Jansky sensitivity. So this is an example of the monitoring data for the last year. In G111, so we have our average spectrum, and then we're following these different peaks to get these time series. And here is G109. Now, some of our sources are actually quite faint. We don't detect them in a single integration. So what we did is we implemented a variable cadence where we average the spectrum to see how bright is the source, and then we have a variable time window depending on how bright it is. This allows us to monitor very faint masers with our small dishes. And if they do flare, which we can then kind of reprocess the data. So then we have day cadence. And then, okay, this may or may not be a flare. The source is low elevation, and we don't have elevation corrections. But let's say we have a flare in this source. We have a big beam, and so we don't know where it is. So we're starting to implement interferometric localization. This is, for example, a 12-hour with 2 antenna interferometric observation. And if you take these 2 portions and you look at their phases, we can actually separate them in the sky. So even though our single dish beam averages over all the sources, we can kind of find their positions. But this is also very much work in progress. And MCA3, which is a 150-meter baseline, just had first light last week. So this is a summary of our workflow. We have automatic observations. We do this variable cadence averaging, and soon we'll be able to do interferometric localization. So in conclusion, we have with 2 5-meter dishes, we have monitored around 60 high-mass star-forming regions, competitive with established 30-meter dish monitoring stations. With cadences between 1 day and a month, depending on source brightness, we're working on calibration. And as we start implementing the interferometer, we would be able to cover hundreds of star-forming regions through this kind of small dish interferometric monitoring technique. Also, there are planned back-end upgrades to our system that will allow us to monitor multiple spectral lines, not just 6.7 gigahertz, but all the maser transitions between 4 and 8 gigahertz. So this is very exciting from a kind of a technical perspective, which will allow us to have a lot of data. If we do find one of these bursts, we can see how all the different maser lines change. Thank you for your attention. Any questions?
Okay, does it work? Does it? No? Perhaps? Yes? Okay, so a quick question to Job. Comments? You don't have any quick?
So are there plans for further MCA antenna?
Yeah. There's a fourth antenna that is in the works. We hope to get land from Helsinki University to build it. But that is a boardroom discussion that is out of my scope. Yeah. Okay, thank you. And I have a handout with more information about our project. You can also find it on this QR code if you're interested. Come talk to me if you're interested in the science, or to Derek if you're interested in the instrumentation aspect of this. Okay, thank you.
Okay, thank you. And then the last talk is Sanna Normo. Now we are going to bursts from young stars to middle-aged stars.
Or rather, I want to today talk to you about radio astronomy, as we have already heard from the previous talks as well, but in the context of the sun and how we can use radio observations to study solar activity and what is happening on the sun. Yes, so the very long title for my talk is investigating the origins of 3 type 2 solar radio bursts associated with the weak coronal mass ejection. And I wanted to talk first about the very basics, so define what are solar radio bursts. The sun is a very bright radio source in the sky, and occasionally we observe these intensifications in the radio emission from the sun. So they are traditionally classified into 5 different categories called types 1 through 5. And this classification basically relies how they look in a dynamic spectrum. So on the left here, you can see sort of an illustration of a dynamic spectrum. You have this frequency and time plane where we can then see these intensifications in the radio emission. The different types of radio bursts have different spectral morphologies, so you can have very different durations, bandwidths, frequency drifts, and so on. What is interesting about these radio bursts is that they are all actually associated with different forms of solar activity. So certain radio emission is coming from sunspots and active regions, also from solar flares, coronal mass ejections, and shock waves in the corona. And in the interest of this talk, and basically what I'm doing, I'm studying these type 2 solar radio bursts. So they originate from electrons that are accelerated by shock waves in the corona. So for example, if you have a CME happening, so you have a big eruption of magnetized plasma coming from the sun, it can drive the shock wave, which then accelerates electrons, and this we can actually observe as this radio emission. So the typical appearance of a type 2 burst is these lanes of emission that drift rather slowly from higher frequencies toward lower frequencies. Also, usually what we do in solar radio astronomy, we kind of flip the frequency axis. So here on the bottom of the y-axis, we have now the high frequencies, on the top, the low frequencies. We often observe these 2 lanes of emission. One is occurring at the fundamental plasma frequency, and another at the harmonic of the plasma frequency. What we can actually now tell from this frequency at which the emission occurs is that the local electron density. So, for example, for the case for these type 2 bursts, when we see this slow frequency drift from high frequencies to our low frequencies, we can actually interpret this sort of the shock moving from lower in the corona to further away, so towards lower electron densities. And well, this essentially makes radio observations of the sun a very useful tool in remotely studying these processes that are happening low in the corona and where these electrons are actually first accelerated. I wanted to also very briefly introduce the main data source for our study. So we're using the low frequency array, or LOFAR for short. It's this, well, low frequency radio telescope. It's operating at the lowest frequencies that we can observe from ground-based observations. So upwards from 10 megahertz to about 240 megahertz. It was developed by the Netherlands Institute for Radio Astronomy called Astron. And so a bunch of these LOFAR stations are located in the Netherlands, where we're using, in this particular study, these Dutch stations. And then we also have a number of different European countries hosting now these LOFAR stations, so to very long baselines. And these LOFAR stations then consist of these antenna arrays. So in each station you have 2 different types of antennas that then we can, the station uses all of these antennas together, and then we can use these different stations to get, for example, very nice interferometry. LOFAR is definitely not a solar dedicated instrument, so a lot of science is being done with LOFAR, ranging from a very wide range of topics. So you have people looking at extragalactic and galactic stuff. Instrumentation is a big thing, of course, for these phased arrays. Also, then people like me who are using LOFAR to study the sun and the heliosphere. Now I'm showing kind of the workflow for this study that we did and how we used LOFAR imaging together with some nice modeling to actually estimate where from the corona these type 2 sources are coming from. So on the very left, you can see the LOFAR data, our kind of snippet of the LOFAR data that we are using. So we have dynamic spectra. And for example, here you see a very nice type 2. So we are using this to actually identify first what kind of solar radio bursts we are observing. And after that, we know, okay, at which frequencies this is occurring, when is this occurring, and then we can actually do the interferomagnetic imaging to actually see relative to the sun where these sources are coming from. So essentially get like a 2D location of where this radio source and where the electrons are accelerated. From this 2D image, we can actually move into a 3D picture of the situation by using some modeling. Here we are using this magnetohydrodynamic model, it's called the MASS model, developed by the Predictive Science Inc., which, for example, gives us these global values for electron density. And if you remember from before, we now know that the frequency of the emission is proportional to the square root of the electron density. We can actually then take these 3D electron density isosurfaces, comparing them with our 2D locations to actually deproject the radio sources. And take a look at also from other parameters given by the model to study the local region and properties of the emission regions. So here is the particular event we're studying. So on 23rd of May 2022, LOFAR actually observed 3 type 2 solar radio bursts within about 30-minute period. On the right, you can see the dynamic spectra of this event. So on the top, I have the spectrum from 1102 to 1122, and then on the bottom from 1122 to 1142. The first 2 type 2 bursts are in the top panel, where the first one is rather faint. It's followed by a bit more prominent type 2, and in my opinion, best looking type 2 is in the bottom spectra. These type 2s were associated with the CME, as you can see from this movie. However, this event is also interesting in the sense that we see these multiple type 2 bursts, which indicates that there was a shock wave in the corona, and it was able to accelerate electrons multiple times. But if you look at the movie of the CME, this is not particularly a very prominent CME. It doesn't look very fast, and it's very faint and kind of dies out. So we wanted to investigate then why do we see such strong signatures of the shock acceleration happening. Then just jumping in, looking at where these radio sources are coming from. On the right, you can see this zoomed-in dynamic spectrum. We have tracked the first type 2 burst with these green colors, and then the second type 2 burst with these teal and blue colors. Then we extracted the imaging at these corresponding frequency and time points, and you can see the results in the 3 bottom panels. And well, essentially in these figures, these colored contours now show where we are seeing this bright radio emission. And as a kind of context, I have also included these extreme ultraviolet images of the sun on the background. So this is the particular active region where we know that the CME was coming from. And when we're looking at these interferometric images of these type 2 sources, we can see that they are coming from a region sort of southwest of this active region where the CME originated. You might also be able to see these little dots in the sort of middle of the contours, and I'm now calling them these centroids of the radio emission or the radio sources, and this is just to get like some kind of point in space that we can then use together with the modeling to see where these radio sources are coming from. And this is obtained just by fitting these 2D Gaussian functions to the radio images. We can do a similar thing for the third type 2 burst. Since it was a much longer duration type 2 than the first 2 bursts, we kind of split the tracking into 2 parts that were the most brightest in the most bright in the spectrum. In the top panel, you can see a little bit earlier part of the third type 2, and in the middle panel, you can see a little bit later part. I've also done this sort of double tracking for this particular type 2, which is, you might be able to see that this single emission lane is sort of split into these 2 parallel lanes, which we called band splitting. So I'm trying to then follow both of these components of the split band. You can see the results on the 4 bottom panels. So the 2 left ones correspond to now the earlier part of the third type 2, and the 2 left ones to the later part. And as you can see, this is now actually very different from the first type 2s that we saw. And well, this already tells us that there was multiple type 2s. The shock was able to accelerate electrons multiple times, but it appears that also at multiple locations. Then we have this 2D picture of this image. We can then take into the modeling, or go into the modeling. This is kind of what our plots look like when we're plotting this MHD model for the corona. So basically, I have this now density isosurface here. For this particular one, it corresponds to this harmonic emission at 72 megahertz. So I'm just using the highest frequency that I'm doing the tracking for, and then here I'm showing you that electron density. And of course, when we're going to low frequencies, then we're also going to higher heights in the corona. The density surface is colored using the Alpine speed values, which is simply calculated from the magnetic field strength and density. So the blue regions correspond to low Alpine speed, and the red regions correspond to high Alpine speed. You can also see this gray sphere. It has a radius of 1.5 solar radii, so to just give you an idea at what kind of heights we're working with here. You can also see these purple magnetic field lines, or these closed loops. They are indeed magnetic field lines. And if I now just play the movie, I have included here now these colored spheres that are our radio sources. And as you can see from this movie, there appears to be indeed this kind of a high density ridge in the corona, characterized by low Alpine speed and these closed magnetic field lines. And I would call this a coronal streamer, so it's this elongated structure in the corona. And these first 2 type 2 bursts, they were coming from a region that was like southwest of the active region where the CME was coming from. And now we can see them deprojected in this 3D image, and we find that they are located in these low Alvan speed regions. Doing the same thing for the third type 2 burst. Here I'm showing you the little bit earlier part. This was very different location in the 2D images comparing to the first 2 type 2 bursts. So it was sort of west of the active region, but again we can see we are still along this streamer structure in the corona, especially in this region of low Alvan speed. And a similar result getting for the later part as well. We're just, again, going to lower frequencies, so we're moving further up in the corona. And what this tells us is that each of these type 2 bursts is now coming from, originating from a coronal streamer, which suggests that, okay, even though we had this kind of slow CME, it's probable that in these regions of low Alban speed, it was able to travel fast enough to actually drive the shock and then create these electron accelerations that we then observe as these type 2 bursts. Just a few take-home messages I wanted to say is, well, first and foremost, radio observations of the sun are a very useful tool in studying solar activity, especially since we can't put currently any spacecraft this low in the corona, and we can actually observe these very low coronal processes from ground-based observations. This study and also very nice recent studies of interferometric imaging with LOFAR have actually shown that these type 2 bursts can be produced from multiple locations on the shock. So the shock can have actually these multiple hotspots for electron acceleration that then creates, for example, these multiple type 2 bursts or more complex type 2 burst structures with multiple lanes. Also, not a new idea, but in fact, these CME streamer interactions seem to be very favorable in creating these type 2 emissions, which also have been suggested very many times. And we have some nice recent results also showing that these type 2 bursts really seem to be coming from these streamer regions when the CME is interacting with the low Alvan speed plasma and actually driving the shock. So thank you.
Okay, thank you. Time for questions. Okay.
Yeah, thank you for colorful presentation. I wanted to ask you about the mechanism of the electron acceleration at the shock. There are various of them, as we heard in the previous talks. So can you please comment on this particular one?
For example, these type 2 emissions, well, maybe I'll go back a few slides. So are produced by this plasma emission mechanism, and well, it's a many multi-stage mechanism, but like the initial electron acceleration, like for type 2s, is shock drift acceleration.
Thank you.
Okay. Still time for another one.
Hi, thank you for the very nice talk. I really love how you connected the observables to the physics. Those models, 3D models, are they somehow derived from concurrent observations?
Yes, so these models that I'm showing, how they are doing this is they actually put like actual observations as like the thing driving the simulation. So they are using these like synoptic magnetograms. So they just take a slice, in like a meridional slice of the sun for about a month, then they put it into the simulation as like an input. And then we get these nice models that they kind of basically show the like large scale structures in the corona, so we can't really say like very locally what is happening, but we do expect them to capture like the big structures in the corona. Yeah.
Very cool.
Yeah,
Thanks.
thank you.
Okay. No immediate other questions, then let's thank Sanna and all the speakers. This concludes the session.
So, very good.
Good afternoon, everyone. Welcome to the session about radiation testing. We start with the head of the Radiation Hardness Assurance and Component Analysis section, Paavo Heiskanen. Isa.
Maybe now? Yes, better. Thank you. Good afternoon, everyone. Thank you for the kind introduction. Indeed, my name is Paavo Heiskanen, and happy to see so many of you here after lunch on the almost last day of the conference. I will give you a few examples on the things we have been doing on the COTS testing for radiation hardness assurance. You see the colleagues below, Francesco Failace and Philip Mund, are the responsible test engineers, and I will be presenting their work. Before we go there, in case the clicker works, yeah, you can just. Yeah, perfect, thank you. I will give you a brief overview of the organization of our section. So on the top right, you will see how we fit into the organizational chart of ESA. And on the left are the main activities we are performing. So our section provides project support in terms of radiation hardness assurance to all ESA projects, all the way from the €1 billion missions to Jupiter to the CubeSats that are being supported by ESA. We also have a component analysis laboratory where we perform failure analyses, constructional analyses on different electrical components, both to support R&D activities and also to support ESA missions and European industries. And finally, at the bottom, the topic that is most relevant for you here today, we have our own in-house cobalt-60 facility for total ionizing dose testing, and we have our laser-induced single-event irradiation facility. Further to that, we have frame contracts with external irradiation facilities, PSI in Switzerland, UCL in Belgium, and RADEF here in Finland. So we are able to perform tests mainly in terms of project support in all of these facilities. And the tests that I'm going to describe to you later today are performed in the UCL facility in Belgium. The main outputs of the work of our section are so-called equipment radiation control boards. These are boards for ESA missions where all items related to radiation hardness assurance are discussed, and to make sure our missions comply, or the satellites comply to the mission requirements. Further, we provide radiation test reports. I will elaborate that a little bit later, but these, the radiation tests like the ones I will be describing now, are available to the public. The reports are available. It used to be just open on the internet, but due to the times we live in nowadays, you have to register and be a European entity to be able to view the radiation test reports. We also provide test reports from our component laboratory, dosimetry reports for total ionizing dose testing, and our main standard, the Q6015, and the relevant ESCC standards are our main deliverables. The 6015 was just updated last year, so it is rather fresh and has the best, let's say, knowledge or our best understanding on how to do RHA in Europe has just been updated. But then to describe a little bit, to give you a flavor of the activities we're doing. The first one that I will describe is an ADC DAC, radiation screening activity. Basically what we did, we took various commercially available ADCs and DACs to see how they withstand heavy ion testing and also total ionizing dose testing. I will be focusing only on the heavy ion testing today. This was an example case that we did on what kind of items should be considered when you're selecting for commercial components. Also, now that we have tested these components, we know that if we see these components in EASE emissions or in industrial emissions, we know that they are probably a risk that either should be mitigated or the component should be changed. Basically, the setup is here. It is a rather large piece of equipment that we needed to take with us to the particle accelerator. It is a setup that we developed at ESTEC. We need the power supplies, the pattern generators, then the microcontrollers, and an oscilloscope to measure the devices under test. In a heavy ion test facility, the tests are performed in vacuum. So we need to connect all the devices under test, do the switching, and we also need temperature control so that we ensure that the tests are done at the same temperature despite of possible self-heating of the components and the associated electronics. And here are a summary of the results. All the full results are available in ESARAD. This is just one ion and one temperature, but this gives you a good overall picture of what the test looked like. Here on the top left, you see a digital to analog converter example of a single level transient. At the start of the test, we measure a certain output voltage, and when a transient happens, the output blips, and then it returns after some seconds back to the nominal value. And here, another example is a latch-up current, because we're also monitoring the device current, and you can see that during the test, the current changes. And now for the results itself. I don't want to promote necessarily European components, but it just so happens that in our test case, the ST component was one of the only ones that didn't provide any effects on any of the tests. For the ones that we are seeing here, also the TI components seemed rather okay, but then you start to see latch-ups. There are non-functional latch-ups that needed power cycling, for example, for this component, and the LET for this test was 46 MeV. And further, in some of the devices, they can be effects that are destructive if there was no mitigation. And then at a final, or let's say the worst possible case for this component, the device was immediately destroyed when it was powered on and when the beam was turned on. So this gives you an idea on the types of effects that can happen in these kind of components. So all the way from it is perfectly fine to being immediately destroyed. And there is really no way of telling that beforehand without doing the testing. And some of them, as mentioned, they can still be used, but you just need to know and understand that these effects will take place and mitigate either with protective circuitry or by other means. The second activity that I want to describe to you today is BJTs, bipolar junction transistors. We had a series of devices where we connected them to an input voltage. We set up an oscilloscope in parallel to measure the output. Here you see a picture of the test setup itself. The components were decapsulated to make sure that the ions hit the sensitive areas of these components. We tested 7 different COTS part types, 6 per sample. And then we also did a laser testing on these devices. Since we have discovered that some of them are sensitive to heavy ions, I will describe this in more detail in the next slide, but then we also investigated them with a laser. Here you see some signal effect burnout effects. You can see the damaged area, which caused the device to fail, and another one you can see here where it burned through during the testing. And we tried to find out if there is a mechanism in these power BJTs that creates single event burnouts, and see if there's differences between NPN and PMP device types for SCE. Again, here is the let's let's say, summary of the test results. If you want to say this in one word, further study is needed. We could not find necessarily any correlations between whether it's an NPN or a PMP device. Here on this column you can see if a single level event burnout was happened and the device was destroyed. Basically, how the devices were tested, we used a different ion, so different LET, different energy level for the heavy ions, and then we started raising the voltage to see at what voltage level does this device burn out. For these 50-volt devices, they both survived, and here you can see the max amplitude of the transient. So for example, here we only saw 400 milliamp transient, and here we got 42 amps. The references you can see here, so for example with a 13-volt bias, the current consumption is rather low, some 100 milliamps, but then if you bias it to 50 volts, you can get these kind of microsecond transients of over 35 volts. Then when we reached these devices that are rated up to 100, 150 volts, and they got destroyed already at 40 volts or 50 volts, we thought that, okay, this is probably where we're going to find the limit of these commercial devices. But then the reference number, device reference 7, 250 volt rated, survived throughout all the way to its maximum rating. Which got us interested. What is behind all of this? And then we started to do testing with laser. So with a laser test, basically you scan the device active areas with a very focused laser, and you measure the output voltage in this case. So you can see where the transients happen. Where is the sensitive area for this energy deposition? Here is a highlight. So the red areas are when you point a laser to the red areas here, you can see a larger variation in the output. It is not a qualifying test. This is just our alternative test method of trying to find out what is causing this difference between all these devices. And we are now gathering information and trying to put an activity together on doing a more detailed test for these types of components. Either by doing a cross-sectional analysis on these areas to find out if it's related to the doping, or if it's related to the different active areas underneath, or if it's related to something else. But again, this is just to give you a flavor and highlight the fact that commercial components, even with very high voltage ratings, can be used, but you need to test them if they are prone to these type of failure modes. And just for my final slide, last year when I was here, we requested inputs from industry. If you have specific component types you would like us to test, we have a survey where you can confidentially input your device types. We are gathering information from the industry to try and find if we see commonalities. Currently, we do not have that much funding available for this type of, let's say, testing that is not related to emission, but we are trying to convince also our management and our member states that this type of testing is actually useful for the European industry. So the more inputs we get, the more data we have to show them that these kind of devices would be helpful for the European industry. And I will share the slides at least on my LinkedIn, and you can also request them for me. I just put some different links to our radiation database, our laboratory, and some further information about our activities. Thank you very much.
Thank you very much for these insights. Any questions from the audience? Several.
Okay, thank you for a very interesting talk. I have a question about the temperature, because, well, I mean, it depends probably on the effect, but we know that, for example, latch-up is more sensitive when the temperature goes up, but it does not, it's not the case for all the different events or effects. How do you choose the temperature? Is it based on some standard, or is it like the worst case, or what is realistically in the mission, or what is the, yeah?
Great question. Indeed, this would depend case by case, and for a very thorough answer, I would have to go back to my SE testing specialist. In general terms, we test the worst case. But in some specific mission cases, we go for the mission temperature as well. But normally, we always test the worst case.
Hello. In the case that there is visual damage on the component, but it's still operational, do you consider that to be destroyed on that occasion?
I have not experienced a case where there would be visual damage, but the component would be destroyed. In theory, I guess it would be possible, but normally this type of damage, you can only see it because it has burned through and the device has been destroyed.
Just on curiosity, since I was in ESTEC 40 years ago to do exactly the same work with a Cobalt 60, and at that time the handling was very manual and simple, no precaution, etc. How are the precautions now to handle this type of things in test?
Thank you. That's a great question, and that's a great observation. Maybe this one is better. Indeed, there are a lot of exposed circuitry, there are a lot of exposed components, and ESD risk is definitely there. And I think this is not only for RHA testing, but for testing in general. My original, or where I started my career, was in automotive safety critical system manufacturing. And I think space industry in general, also at ESTEC, but also what I've seen is in industry, all of us have a lot to learn on how to handle devices and tests with the required care.
If you reserve the Cobalt 60 facility at ESTEC, can you also provide the supply current monitoring for the experiments, or do you have to do that yourself as a visitor?
We have the capability to provide the monitoring ourselves. We have the necessary test equipment. Maybe I will just show you for that context this link down here for our TPAs, or third-party activities. So all of our Cobalt 60 facility and also some of the external facilities are also available outside of ESA contract through these third-party activities. So basically we charge the costs to us plus our administrative overhead, and you are able to use our facilities and equipment if you just have one-off testing that you want to do. Yes, they are available.
One more question, but then we need to move on with the schedule here.
Okay, one question. I saw that you made your own test bench. Why don't you use commercial test equipment for that, which are more standard?
That is also a really good question, and it is something that we are actively working on, how to do less tinkering, how to have a more generic test setup. And I think it's normally because I am describing very simple devices, but when you test really complex devices, you usually need to test them in the application condition or in the worst condition. So that's why we normally use let's say tinkered setups, but it's a good point, and it's something that I aim to improve, that we should have a generic test setup available for different actors in the industry. Thank you.
Yeah, thank you very much.
Thank you.
Yeah, I assume Pablo will be available for questions also.
Yes, of course. Yes, I will be here.
Yeah, Next on stage, please, Janne Holma from VTT.
Hello, everybody. So my name is Janne Holma. I'm a researcher at VTT, and I will basically present the work of our team. Especially people who have been involved to this are Juha Rauhala and Antti Näsilä. And we also got the expertise from ISA to these tests. Cesar Paatelo-Polo was giving us expertise and guidance for the second test campaign which we did. And so the title is Radiation Hardened Testing of NIR, Near-Infrared Image Sensor for Comet Interceptor Project. There is actually, at the same time, another kind of status update presentation given by Antti Näsilä in another lecture hall. This is more specific about the radiation test. So the agenda of the presentation is as follows. So at first we'll take just a very, very quick glimpse for Comet Interceptor and MIRMIS instrument. And then I will tell you about the preparation of the radiation test and test setup. Then we'll take a look to heavy ion test campaigns which we did at the RADE test facility in Jyväskylä. And then, so the results, the estimated probabilities of Cs, and finally the mitigations means to reduce the risk of C-induced malfunctions in the mission. So the Comet Interceptor mission is the first mission to visit a long-period comet. So the spacecraft will be placed at Sun, Earth, Lagrange 2 point to wait for a suitable comet for some time. The scheduled launch date is currently starting from late 2028 up to June 2029. The MIRMIS instrument of the main spacecraft includes the near-infrared hyperspectral imager for sphere range and the middle infrared spectrometer for range. And these are supplied by VTT. The mission is the fast class, so F-class mission, and the requirements for the electronics are according to ESA class 3 mission. It basically means that for COTS components, the construction analysis were required, and then radiation evaluation of some of the electronic components. These were partially made by ESA at ESTEC, and then we have tested that image sensor. The near-infrared channel of the MIRMIS instrument, basically it's a hyperspectral imager for sort of very infrared range, and it's based on the VTT's Fabry-Perot interferometer technology. The image sensor is manufactured by SCD, and it's type Cardinal 640 Loon, so low noise kind of version of the Cardinal sensor. It's one of the state-of-the-art sphere sensors currently, and it's not pure COTS components. It's tested partially according to MIL standards, but there is not enough published space heritage to use it directly in this mission, and therefore radiation evaluation is required. That's a project-specific requirement. The reference for the radiation hardened testing is the SCC document 25100, so the single event effect test method and guidelines. The effective operation time of the near channel in space is about 30 minutes, but it's rather short, but it's really crucial that this instrument will be working at that time. Here you also see the CAD model of the MIRMIS instrument. It's this entity here. So before the test, we prepared the test setup. So we have chosen 3 sample sensors, and the glass windows were removed because the penetration depth of the ions is less than the thickness of the glass, which is roughly 1 millimeter. We also prepared the hardware for to basically control the devices, so the readout electronics for the image sensors, and prepared test equipment for it. So basically, we had a power analyzer with programmable overcurrent protection. We expected to see the following single event effect. So first of all, possibly, let's say in bad case, single event latch-ups. So basically kind of like parasitic short circuits in the structures. And then possibly single event functional interrupts, so CEFIs. We developed a software for detection of CEFIs via readout electronics. And we also prepared the trigger output to shut down the beam in the case of a cell. We couldn't get any preliminary data of the sensor, basically about the sensitivity of the sensor to cells or CEFIs. We asked that a couple of times from the manufacturer, but they were not very responsive. We also planned that and kind of defined the preliminary schedule for the test because we knew that we will have 1 or 2 6-hour slots at Friday for that. It was a very tight schedule. Here you see an image of an image sensor, which is deleted, just to expose the active area and the readout electronics, which you see here, it's blue, to the radiation. So, as I said, we had 2 test campaigns. In total, 15 hours of beam time, of which probably like 10 to 12 hours was effective. We used that 16.3 MeV ion cocktail, with which we could reach theoretically that 62.5 MeV kind of energy level, or sorry, linear energy transfer level, which is the kind of immunity level according to ESCC standard. The beam cross-section was tuned to cover the active area of the sensor and also the readout electronics behind it. And the samples were kept in air, not in vacuum, in a dark test chamber at room temperature. And we captured frames from the image sensors continuously during the tests. So in the test campaign 1, we identified several types of CEFIs and 2 cell-like events. Probably not exact cells, but something. We had a quite low threshold limit for the overcurrent protection system that time, and so it triggered immediately and cut basically the VCCs off. And our attention was drawn mainly by kind of very drastic displacement damage, so our sensor worked very well as a particle detector, and that was quite a surprise. So we spent quite some time for kind of studying residual effects, not really the cells or CEFIs. So then in test campaign 2, we were more focused on purely on the identification of cells and CEFIs, especially the most severe CEFIs, which basically caused the sensor to freeze and stop the image capturing. And we could use, anyway, the same sample sensors in both tested, so we didn't destroy them completely. Yeah, sorry. So here you see the test setup with 3 devices under test in the test chamber. So some observations of the test. As I told, we identified several types of CEFIs, so row and column defects, for instance, bright or dark rows or columns, or cluster of bright pixels, etc., and also sensor freezing. Here you see a GIF animation of one of the runs. So in the beginning there are almost nothing, and then there are some bright spots, and some of them may remain over a longer time. So we would take a couple of frames and some of them persist over for a couple of frames. So those pixels are basically inactive in the next captures. We also detected cells by the power analyzer, but also we captured images in which we had cell states on. So the sensor was still working despite that there was effectively a cell and a high current state. We also had plenty of secondary effects caused by displated damage and total ionization dose. So the dark current obviously increased, so we lost the sensitivity of the sensors. And we also see the loss of active pixels. They just remain bright. And also like random telegraphic noise, so the pixel value changed just randomly after the tests. So here are the summary of the beam runs. So our goal was to, with every single ion, go up to 10 to the power of 7 fluence. But we couldn't do that with the higher LED values, just because we have so many effects and we hadn't completed the cell detection. So we can see that actually the sensor, unfortunately, is very sensitive to cells at high LEDs. So basically, starting at roughly 30 MeV, we could see that almost every single particle could cause a cell. However, the resolution of the particle instrumentation was poor for smaller fluences. So the minimum feasible particle flux triggered the cell in every 1 to 3 seconds. So when we start to beam, we had a cell. And so we don't know exactly that if this number was even lower. We have just 150 particles, and we have 20 cells which were detected. So it's quite a high number. But anyway, we could recognize or identify the safety thresholds. It's the most important parameters, and some kind of guess of Cepheid and cell saturation limits. Also, regarding the Cepheids, they were possibly masked by the cells at high LEDs because those total fluences were so low, so we couldn't identify any Cepheids at these LED values. But the total fluences were so low that might be that we didn't see them, or we couldn't identify them because we had a cell states on. So we defined the threshold and the saturation cross sections for cells and most severe Cepheids. And here are the numbers. So the threshold for the cells is about 6 MeV by mg divided by cm2, so those units. And basically, what's probably one of the most important things is that all cells even triggered the same VCC line. We have 4 VCC inputs of the sensor, but all of them triggered that plus 3.5 volt input line. And when we discovered the cell, when we saw it to happen, we switched the VCC lines off, but we didn't switch the data lines off, the readout off. But anyway, the cell state was always interrupted with this method. So the data lines itself couldn't maintain the cell conditions of the sensor. So regarding the Cepheids, as I said, we only concentrated on the most severe Cepheid types, which basically stopped the image capturing. The threshold was 2.6 units. And the estimate saturation cross-section, you see them here. As I already mentioned earlier, this is probably lower than the real value. It could be closer to 1. It's already quite high in this image. Anyway, it can be even higher because just our total fluence was so low. And as I mentioned, those CEFIs were possibly masked by very frequent cells at higher LEDs, so this value might be also slightly higher. We also complete the C-rate estimates with OMERE simulation software. The reference for the radiation environment in space was the CDF study report of September. And according to that, the radiation environment is very comparable to a stationary orbit. So the electrons which are right there should be okay for as well. So we estimate the proton rates with profit and sigma models. So the cell event probability is in the order of 1 event in 86 hours with the kind of identified saturation cross-section. But as I mentioned, this might be actually higher than the value as we saw in the measurement. So I also run the simulation just using the value as the worst case, so up to 1, and in these cases it was 1 event in 12 hours. Just one slide left. And the CEFI event probability was 1 event in 1.3 years. But anyway, those both events, if seen in space, are very bad for the mission. Therefore, we studied the means to mitigate the risk of this. So basically, we implemented detection protection circuits in the design in order to not shut down the near miss instrument in the case of a cell. Just shut down the sensor and flag upstream that there was an error. And then regarding CEFIs, we will apply soft reset before capture of every frame in order not to lose any captured data. Thank you.
Thank you very much for sharing your results. You're a bit behind schedule, so we have one question maybe? Yes?
As far as I know, heavy ion tests are normally performed in vacuum because the air in between reduces the energy. So why did you decide to use ambient testing, and how do you think does it affect the values measured?
Thank you very much. Good question. We consulted the RADEF facility, and they said that in our case, we estimate that penetration depth is still in certain range which can be done in air. So we don't lose much of the kind of the penetration depth if we have the samples in air and close to the beam window. So I have it. There was that data given by the facility in which there are estimated penetration depth for that ion cocktail with different degraders. And in the same diagram, there is also like mention about if the sample is in the air and what's the reachable LET and what's the penetration depth. Thank you.
Thank you very much. Yeah. Next we have Alla Marchenko from ASRO.
So, hello everyone. My name is Alla Marchenko, and I'm a test engineer at ASRO, and we are delivering instrument for ESA program. So it had to go through very thorough RHA process. So today I'm going to be talking about the radiation hardness assurance activities and capabilities at ASRO, and what are the lessons that we learned from this Repe Henon project. So let me start with the mission overview. So our instrument is participating in HENAN mission, which is Italian deep space mission that aims to travel to distant retrograde orbit. And the main objective of this mission is to demonstrate near real-time monitoring of the space environment. As I mentioned, this mission is a part of the ESA GSTP program, and HENAN will be launched in January 2027 with Ariane 6 rocket. So here is the instrument itself. If you visit the poster session, you might have maybe seen the poster with it. Our instrument is called REPE, and REPE is a relativistic electron and proton experiment, which is a compact solution for electron and proton monitoring. And here I also have the energy range that REPE is able to detect. So for electrons it's from 0.25 to 10 MeVs, and for protons it's from 2 to 500 plus MeVs. Instrument consists of 4 electronic ports and 4 detectors in stack, and it is 1 unit in size. It was developed at ASRO in collaboration with University of Turku. So yeah, as we all know, there's plenty of radiation in space, and the main sources of that are galactic cosmic rays, solar particle events, and radiation belts. And space is dominated by protons, electrons, and heavy ions, which can cause different kinds of malfunctions or even destructive effects on electronics. Total ionizing dose, displacement damage, and single event effects. So in order to assure successful mission and the functionality of the instrument throughout the whole mission, each instrument has to go through a very thorough RHA process. So RHA process starts with the careful selection of the components and trying to find the available experimental data that would be in compliance with the RHA requirements. If there's a possibility to find that data and use it for our component, then the part can be accepted. And in case if not, then we have to think about the alternative part that would have this kind of information and fulfill our RHA requirements. So if the substitution is feasible regarding the cost, schedule, and effort, then a part can be substituted and we can move on with our lives. In case if not, then we have to think about the dedicated test campaigns that could be done to initially chosen component. And if, again, the test campaign is feasible regarding cost, schedule, and effort, then we proceed with the testing. In case if not, actually in both cases, either we go to the test or not, we have to think about the possible failure effects and how to mitigate them, or do the analysis if those effects can be tolerated by the design in the first place. In some cases, that's actually possible. In case if yes, we go to the left, so part can be accepted with these proper mitigations, and in case if the mitigation is not possible, then we must reject this part and redesign the instrument. Here I also, in the small box, I have a list of radiation effects that have been tested at ASRO. So we have tested single event latch-ups, single event upsets, functional interrupts, and we also have done DID analysis. So more specifically on that, what are the actual RHA activities that we do and we have done at ASRO? So as I mentioned, each RHA process starts with the careful selection of the component, and we try to find experimental data for them. So with this experimental data, so this was also a case for REPE HENAN project as well. So with this experimental data, we ran simulations with OMIR to estimate the error rate in order to calculate the availability of each critical component. So the availability is the percentage of time that the component is going to be functional during this specific mission. Via this information, we calculated the availability for the whole instrument to ensure that it will be functional enough. After the analysis, we moved on to the actual testing. So due to insufficient amount of the experimental data for one of the REPE HENAN component, we had to proceed with the component level testing. So we did test this component individually with the heavy ion beam, and the test has been performed at RADEF facility in Jyväskylä. After we closed the subject of the component level testing, we moved on to the board level testing to verify the overall functionality of the whole instrument. And that we did with the proton beam, and the facility we chose for that was PSI in Villigen. So, what exactly happened during these tests? So the scope of the component level testing was to verify the functionality of the ADC under the radiation in high temperature. And here on the right picture, we can see our test setup in RADEF facility. So this picture has been taken in the irradiation room. So we have our, I don't know if you can see it, but you have to trust me on that. So we have our DUT mounted in front of the beam. Then we have the heating gun that would point directly to our component. And with the infrared camera, we would verify throughout the whole experiment that the temperature is high enough for our requirements. So the component was irradiated with krypton ion with LET of 39, and for specific tests, for the single event latch-ups and destructive test, we used temperature of 80 degrees. So yeah, as mentioned, with this test setup, we managed to do single event latch-up testing. We also did the soft error testing, and in the very end, we did the destructive test to verify that that our component is going to be recoverable after a long period staying in the latch-up. So during the whole measurement, we fed almost sinusoidal input to the ADC, and we constantly measured the output signal. And if there was any deviation between output signal and input signal, the software that we used automatically triggered the capture of the output signal. And in the post-processing, we saw a segment of that output signal, including the error that caused this capture. And the software that we used was specifically developed for this test campaign, and it allowed us to monitor the output signal and also to control the DUT itself. Also, again, we cannot see anything from the small text of the software, but we also managed to count the errors that comes from each channel. So we monitored all 8 channels of the ADCs, and then we also had the counter for total error rate. Okay, so we did the component level testing. Everything went well, and the component list was verified. So we moved on to the board level testing. And the scope of that was to verify the functionality of each PCB under the proton radiation of 200 MeVs. So our instrument itself is it consists of 4 electronic boards. So 3 of them are full-sized boards that are in stack, and then we have a 4th smaller board on the side. So in order to actually test each PCB individually, we had to disassemble the instrument and then assemble it in the planar configuration. And that way we managed to irradiate each board and to characterize them one by one. Here, again, we can see our test setup. So our DUT mounted in front of the beam. This was in the irradiation room, and this is the view from the control barrack, from which we controlled the position of the beam and DUT, and also controlled DUT with the PC software. This software was also developed specifically for this test campaign, and it was tailored to its need. So with this software, we constantly acquired the housekeeping data and monitored the device. So in case if there was any problems with the device, then we saw it in this window, and also in the post-processing of the saved data that has been saved with the help of this software. And yeah, in conclusions, after post-processing, we only saw very minor issues, and these were eventually mitigated by the design. Okay, so in conclusions, at Astro we have successfully performed radiation testing and radiation effects analysis in accordance with ECSS standards, including the availability analysis and the TID analysis. And each test was tailored to specific mission requirements. and also included the development and configuration of dedicated software and hardware. Here I also present the overall RHA process that we established at ASRA, so starting with the component selection all the way to the ESA approval, learning different skills like heavy ion testing, proton testing, and performing different kind of analyses along the way. So here I pointed out the TID testing, which in this project, in Repehenan project, we did not do because the TID analysis was thorough enough to see that all the components are according to mission requirement. So yeah, the project provided a lot of good learning opportunities for the whole team, and hopefully we improved our abilities to the future project as well. Well, thank you very much. If you have any questions, you know where to find me, here. And then if you're interested in our technology, then please scan this and visit our website.
Thank you very much. We have time for one short question, maybe? Something urgent? Okay, maybe from my side, the software that you developed, is this like your proprietary in-house, or are you? Yes. Yeah.
Yes, the software was developed in-house, so it's.
Okay, and I guess that's your company secret that you're not going to share, or?
What do you mean?
Are you going to share the software?
I don't think so for the open usage, but yeah, probably cannot talk a lot about that. Promise you too much.
Yeah, I would be interested, but thank you. Then, yeah, next on stage we have Jonathan Silva with a compact dosimeter.
Hello. Hello. So today I'll be talking about the design and radiation testing of the compact dosimetry system. So this is the dosimetry system that is designed to measure the radiation-induced damage that happens onto the semiconductors inside the avionics, which is shielded from the external environment. So the concept of this, this first concept was first talked about here in the Winter Satellite Workshop by Mr. Palaver last year. So then we talked about, okay, let's design an instrument, and then here we are. So a little bit of the background about the environment. So you know that we have the radiation belts around the Earth. There are multiple radiation sources from the trapped particles, from the solar energetic protons, gamma rays, and which is again very dynamic. It changes based on it changes based on how the sun's activity changes. We have different levels of the let's say particle fluxes in different orbits. And before we started this, we went a little bit about what have people done. So because we were looking at the TID and the displacement damage dose. So there are a couple of previous, for the TID we have this, the only available commercial sensor, which is the RadFit by Varadis, VT01. So it's a no-brainer, we're going to use that. And but for the DDD, there are any commercial sensors. And then looking at the past efforts, there have been some efforts from 1990s. So there are people who have been using gallium arsenide LEDs, photodiodes to see if it can be turned into a displacement damage dosimeter. So there have been two different methods that I've found. So one used a custom gallium arsenide photodiode, and then they were just measuring the change in the dark current, and again with the and applying temperature compensation because the temperature changes the dark current on the photodiodes as well. And then the other was using this light output. They're monitoring the light output of the LEDs, and then using the frequency-based method to get the fluence, the level of the DDD out, which is slightly more complicated. But we wanted it to be simple, so we're just monitoring just the change in the current or the voltage as the displacement damage increases. And so before we started developing the instrument, we wanted to have an idea of, okay, what is the displacement damage that we want to monitor, or what would be the minimum one. So we did a couple of spin-based simulations for a couple of 3 orbits. As you can see here for the ISS, for the SSO, and the GTO orbit. And we added just a standard 1 millimeter aluminum shielding for the external shield, so we can remove the very high level of NEEL. So what we got was we wanted this came out to be our like standard one for SSO 1 millimeter. So we get around like 1.9 10 to the power 7 MeV for silicon, and since we are using gallium arsenide, and that's what we were concerned about right now, so we get around like 9 into 10 to the power 6 of MeV per gram of displacement damage for the gallium arsenide, and that is our like minimum measurable change that we want to observe. And then we set a couple of objectives. So first, obviously, we're going to measure the TID and the DDD. And the next one, like because since we don't have any commercial solution for the DDD, and we have to make our own sensor, so we also added, okay, we'll measure if there are the COTS LEDs that we find, which are similar to the ones the previous attempts used, are sensitive to the DDD, and in what kind of operation mode would we get the results out, and are they even sensitive enough to be used as a sensor? And then this led us to the LED screening test. So we selected 8 LEDs, which is of course which has the combination of gallium arsenide and gallium aluminum arsenide, and each of these 8 LED different types had like 5 of them onto a board. You can see like in this area we mounted like soldered 40 LEDs. There are like among these 5, like 2 were in forward biased readout mode, 2 in reverse biased, and 1 was like completely grounded. We're not reading it out during the test. And we had this relay matrix. We had this relay matrix for switching for the forward bias, because we're only using 2 current sources for forward biasing. We chose at 100 milliamp and 50 milliamp. This number came based on the data sheet of the peak current the LEDs could support. And we had like a couple of diagnostic pins, like 40 pins output, which just connect to a big multiplexer to collect the data. And this is the final screening board which we were sitting on the beam. And then, yeah, the LEDs are not visible because it's covered by a masking tape, because we wanted to block out any X-ray lights that would trigger the reverse bias diodes. And alongside, we also made initial, let's say, prototype of the dosimeter, and then we added a rad fit as well there. So just test out like, because this one does not have a rad fit, and we were just adding, let's just see how it performs on the test. And the irradiation test was performed in Scandion Clinic in Uppsala in last year. It's a medical proton accelerator, so this resulted in us not being able to get like very high fluence that we would have liked, because they were like limited. They gave us a limited amount of the 64 MeV beam, so we got around like 1.5 into 10 to the power 11 protons, so that's like 50,000 MU, 100,000 MU of irradiation, and we were monitoring 60 voltage channel using using this DAC, which is the Azilent multiplexer. And then we had a, you can see here, we had this is our multiplexer, the power supply, and this is the computer where we're running the Python script, which is controlling all of this instrument, getting the readouts, and then saving it online and offline, a couple of backups. And this is the results that we got. So this is the sample result for 1 LED type. So this is the pre and post irradiation biasing. And we're just looking at like which point has like the most sensitive, like which was the peak where the current changed the most. And we found like it was at around like 1.05 volts for all of the LEDs that showed the change in the forward bias, forward current. Like there were a couple of LEDs which were like pretty flat. There was not much change that we found. So we were only including the ones that have the change. And we also saw like 2 of those LEDs among the 8 had like some measurable change on the reverse current as well. So as you can see here, like also one thing was like beam was not that stable, because it is just being triggered because of this radiation safety system inbuilt. So we can see like there's like, you can see like there are like some flat lines here, and we had 2 irradiations. So one was done on a small area, same dose, so we have like a bit higher concentrated, higher change here, and one was a bit spread out, so we have like less change. And the total current leakage that we saw was like 3.75 nanoampere, the maximum change that we recorded for 2 LEDs, and this is the other LED. So that was the fluence of after the first irradiation, and then after the second irradiation we got this much there. And this is for the rad fit. So even in the rad fit we have like a very nice change for the total ionizing dose recorded. That was on the furthest away from the beam. And so this is the summary of the table for the changes that we recorded for all the LEDs. So as you see, like this is the LEDs that I had like on the graph earlier. So it has like a 2.2 was like the peak change that we recorded at 1 voltage, but on the reverse current, it was like there's almost no change at all, almost flat line. And there were some LEDs which are like 0.15 nanoampere change, and some went like negative 0.2 as well. So and only these two LEDs, like one at 3, one at 3.75. And ultimately from this table we chose the 5 LEDs. So these are the ones, and among these first three, we are reading them out in the forward bias mode, and the other two in the reverse bias. And since for the second test we're going to use a lower energy proton beam at 10 MeV, we had to like file out the extra resin or the encapsulation for the LEDs, otherwise because the beam will not reach the sensor. So we kind of like filed down the diodes, like chopped up half of them. So as you can see here, like especially these two, and then these are also a bit down. And then here comes now the instrument design. So before we start the instrument design, we had to have some requirements. So the most of the requirements for us comes from the 4-cell platform that's developed in Alto. So that's the model of the 4-cell satellite. So the, on the power side, so we had like 8V4, which is the battery voltage, completely unregulated. It fluctuates based on the battery voltage of the satellite, and but the current is the maximum capped at 2 amperes. That's the peak current we can get, and the voltage changes. And the other is 3.6 volt at 1 ampere. So that would be used to power up the whole design. And for the communication, we have like the 4-cell platform provides RS485 connection, the 2 pairs, one for redundancy. And for the size, like let's say the requirement was make it as small as possible. So yeah, we have like it's set at like right now at 45 by 55 millimeter board. And for the TID sensitivity, again, so this is based on the RadFit, because that's the only thing, that's the only sensor we have, so that's the sensitivity we are going to get. And for the displacement damage, so again, the minimum sensitivity, like as I mentioned earlier, from the simulation from SpainBase, so that's the minimum sensitivity we want at the sensor. And for the maximum, we wanted it to reach at least for the GTO orbits level, that's 2 into 10 to the power 8 MeV of damage. And the measurement, like since this is, we are just measuring the total dose, we're not monitoring the live one, so we're just doing, reading out 1 measurement per day. So that means it's a very, very low duty cycle. And it's also, the sensing is done passively, the meaning when the sensors are collecting the damage, like we don't need to bias them, they're completely grounded. And only in the readout we're biasing, so it's a very low power consumption as well. So a little bit of the electrical design. So we have like, so these are our like diodes that we chose. So this one is the forward one, that's the reverse biased. So for the 5 diodes, we made 3 boards. So each of them had like 1 forward, 1 reverse combination. And we are using a operation amplifier based voltage source here. And then all the readout is done by the STM32 microcontroller. It has its own 12-bit ADC as well, which makes it easier for us. We don't need any extra devices for that. And we also had like a couple of diagnostic tests going to just monitor it by the external device to verify what the microcontroller collected and make sure it's correct. And this, if you see this circle, that was the area that was irradiated after watching the test. I'll come to it as well. So the circle points out the sensing part, and that's the RadFit there. And yeah, that's the final assembly of the board. And as the size is 4655, we have it's powered by 8V4 unregulated and 3V6 regulated. The peak maximum power is 0.3 watt for this. And electrical design. So this is the forward one. So we are putting the LED here, and this, as you see, it's like just to make sure that there are no current leaking from this point into the other part. So we have like, let's say, as less of the leakage current as possible when reading it out. So, and this, there's like a stable reference voltage, and then we are using the op amp to maintain the bias voltage at the anode end of the diode. And the reverse biased is, so for the forward biased, we're fixing it at 1.1 volt because we just wanted to go a little bit off from the peak. And for the reverse bias, reverse bias also uses the same system, but it uses at 5 volt. We're using a new 5 volt reference for this one as well. And as I mentioned earlier, the readout is done by the ADC as well. Okay, so a little bit on the proton test. So we did this testing at Helsinki Accelerator Laboratory in Kumpula. So it has the tandem Van de Graaff generator. We are using 10 MeV proton beam. It has the scanning diameter of 25 millimeters, so that big circle within which all the sensors were placed. And for this one, we had since we had 3 different boards, we did 3 runs. So this is the vacuum chamber where the boards were set up. This is the board inside the chamber, and we had the instruments here to collect the data. So what we did was we started with board 3. So board 3 had the least amount of protons. So, and it had the smaller steps as well. So this was more testing as well as seeing what the accelerator can give, the minimum, let's say, measurable fluence that we can get. And then the board 2, board 1, and then the board 2. So yeah, for this one we monitored the 18 channels from the board using this same multiplexer we used for the LED screening. So it was this Azalane 34901 multiplexer board. And there was also another Linux PC running a Python script which was operated over remotely from the control room. And this is the results for the forward sensors, for all boards. So what we noticed was the first board that we irradiated, which was board 3, and it's represented by the blue curve. So that's the total current, that's the current changed we noticed as the fluence increased, meaning as the damage increased on the LED. And there was this point where the current got saturated at one fixed point. So that is limited by the electrical design itself. So, and then we noticed that the voltage started dropping. It's the triangular curve. You can see it's similar to how the current changed. Similarly, the voltage started dropping, and we went up to until 2 to the power 10 to the 9 of damage for the board 1, and for the board 3, and for the board 1. So board 1 is the red one. So these are all for different LEDs itself. So all 3 are different LED sensors. So what this means is board 3 is the most suitable one to use as when we want let's say a bit more sensitive measurement for the lower dose, and if you want a bit more coarse, we want to let's say get once every 6 months, and we can actually use the other ones because they are a bit less sensitive. It can accumulate more dose. And this is the readout from the MCU, so that the MCU ADC collected. So this is actually pretty similar to the one that was collected by the DAC instrument. And this is for the reverse current. So now this part is a little bit interesting. So what happened was we did not see too much of a change. It's very minute change here. If you look at this, it's in the third, fourth digit from the microampere level. So and for this red and blue curve, they are the same LEDs. But then what's different is the blue one had a smaller increasing influence, and the red one has a bit larger step. So you can see the red one just jumps off. And from this, what you also noticed was the new 5-volt reference that we were using, it kind of failed for the board 2 and board 3, board 1 and board 3, but not for the board 2. So you can see there's this sharp drop in the voltage threshold for the reference. So it kind of went from 5 volt to 4.1, meaning we cannot really use this one now. But then it's surprisingly for the other board, the last one, it's pretty stable again. So, and this is the data collected by the RADFIT, which was actually right next to, or next to on the voltage reference chip. As you can see, on the board 2, we don't have much of there wasn't any reading we could get from the RADFIT because, and for the board 1 and board 3, we had at least 1 centigrade of this TID measured. So meaning maybe the RADFIT was not illuminated for the board 2, and then the voltage reference did not fail on that one. So all in all, the design of a initial version of a dosimetry system is done. So it measures TID, DDD, and we can see that the gallium arsenide LED can be used for the DDD sensor as well, and it's pretty sensitive. It's just the one that we find on the market right now. And for the future work, we plan to integrate LED detector onto this one as well, so we can just place it wherever we want. We get 3 different kinds of reading. And yeah, we're looking for a satellite to fly this instrument if anybody would be interested to have this instrument on their satellite. Thank you.
Yeah, thank you very much. We're quite behind schedule. You're available in the coffee break?
Yes, I'm available in the coffee break.
Okay, and then next up, I'll invite Maximilian von Unwert to the stage. Yes.
Thank you so much. Just left and right? Should be pretty simple. Okay, it works. Thank you very much. I know I'm between you and your coffee break, so let me just talk about our current mission, the Tacheles mission. And therefore, I would like to introduce you to our company, to Neurospace, how we got under the seats of the Artemis II astronauts, and what that all has to do with rovers. So this is part of our team. Neurospace was funded 2020 in Berlin, in Germany, by Irene Salvanathan, the third person from the right on the left picture. And right now we are 25 persons working on rovers and on satellites from really recently. And this is our team at the SLS rocket in the USA. And we're really excited to see the current pictures of the SLS rolling out at KC, and we're really excited for the launch of our satellite, which is integrated into that great rocket. Before I talk about that mission and why we do that when we build rovers, I'd like to bring you to the moon. That takes not that long to go to the moon. We would take around 3, 4, maybe a few more days, so it's not that far away when we want to go there. I mean, there are not that many missions flying to the moon right now, so you have to have your opportunity to go there, but then it takes us just a few days. In comparison to Mars, where we want to find life and do a lot of cool things, it's really, really short. So as Matthias Maurer, our German ESA astronaut, put it quite nicely, the moon can be our stepping stone to Mars. So we can learn technology at moon directly in front of our door before we even go to Mars and do things there. What do we experience when we go to the moon? As I mentioned, it's far away. That is also a problem when we think about how much does it cost to bring stuff there. So around a kilogram costs around €1 million. Really depends on who takes you to the moon. Then we have 1/6 of Earth's gravity there. That's cool when you want to feel light. We have long days and nights that delivers us with a pretty big temperature delta of around minus 180 degrees Celsius to plus 120 degrees Celsius. We have nearly vacuum. There's a nice anecdote about that. When the Apollo astronauts arrived at the moon, they brought more atmosphere to the moon than it is actually there. So I think it's really okay to say it's nearly vacuum. We have no magnetic field, so no protection from radiation like here on Earth. So no auroras. Did you see any auroras here in Helsinki? It's too cloudy, right? So unfortunate. My colleagues in Germany saw auroras, sent me cool pictures, and yeah, okay. Then one also very important thing is that the lunar surface is covered with regolith, and this regolith is very abrasive. So when you bring robotics, when you bring mechanisms to the lunar surface, you have to be very careful because this stuff gets into everything and clogs your systems. We came up with our Hive rover to overcome all of those challenges, and we are really, really far with that. And we hope to launch our rover in the next few years to bring it to the moon. You could do a lot of cool stuff with that, not only science exploration. I think this is the first thing you really think about when you think about rovers. We also think about much more like logistics, building up infrastructure even before astronauts arrive on the moon. Really training what we would need for further missions like on Mars and even further beyond. This is our timeline, and I want to shortly introduce you how we developed our rover, because in the beginning it was pretty straightforward. We started building rovers, and it was 2 or 3. In the meantime, 3 years ago that we sold our first rover to DLR, to the Lunar Analog Facility in Cologne, where they want to train astronauts for lunar missions, and therefore they needed some rovers so that they can also train robot-human collaboration, and that's where we sold our first rovers. Good for us, because then we could also, or we must also make our lunar rovers regolith-proof, so we can also put a check mark on, okay, our rover is regolith-proof. Next, we even improved our system, and then by beginning of last year, we split up our company into two separate departments. One department facing on terrestrial rovers, because it's pretty straightforward when you build rovers that there are a lot of industrial applications where you need robotic system to transport stuff from point A to B. But we also took care of bringing our rover to another TRL and finally bringing us to the moon. And this is why I want to explain you these two missions and finally this mission, which qualify the next systems. So here we have a rover which is already regolith-proof, but mechanics can't work in space, electronics can't work in space. That's why we needed those missions. And the first mission I would want to talk about shortly is the Hemera mission, which launched with the exploration company with the Nix capsule last year, and was a great success for us because in this blue box, unfortunately I do not have cool pictures what's inside here, but I try to explain it, is especially the suspension system of our rover, and we put it on an endurance test so that we can now really say, okay, the hydromechanics, so all the mechanic parts of our rover survived space, survived the launch, and are still working on space. Of course, we know that we also need to land on the moon, and originally it was planned to get the experiment back, but you might know that unfortunately the exploration company's Nix capsule crashed during re-entry last year, so we didn't get the experiment back. We just have the data which we can could generate on board in space, and we just know it worked in space after launch. That's great, and we can say finally, okay, hydromechanics work in space. What about the electronics? This is why we came up with this big mission and built our first own satellite to qualify the electronics and also software, the mission control for our rover inside of a secondary payload of NASA's Artemis II mission. So in the last 18 months, it was a pretty fast build of the CubeSat, and with very low budget. We put our satellite together with a lot of partners from Germany. I think also some of them are in the room here. Thanks for all your support, all your help, and we are finally excited to launch our satellite in hopefully 2 or 3 weeks, depending if NASA can hold that launch window. We will see. Shortly about where we are and how our mission looks like. So we are located in the Orion stage adapter, right underneath the Orion spacecraft, so right underneath the seats of the astronauts. That's also why we had quite a lot of requirements to fulfill, and that wasn't easy. So it was a hard time the last 1.5 years, and we are now finally, this is actually a picture of the team integrating the satellite into the staging adapter. What happens then when we are launched? We unfortunately do not get around the moon or to the moon, but very close to the moon. So we will already be deployed here. Here, the interim cryogenic propulsion stage will kick the Orion orbit to the moon, and before they will deploy the secondary payloads, so also us. Unfortunately, and this was quite a big problem, the ICPS will perform a disposal maneuver before they deploy us, so we had to bring our own propulsion system to raise the perigee at least as high that we hope we can survive and get a mission time of around 2.5 years. So this is what we plan. What do we do there? We have 3 primary experiments, 3 primary goals. As I mentioned, we want to qualify our electronics if it can survive outer space. The great thing of this is we are really getting out of the Van Allen belts and experiencing quite a complicated radiation environment, and we did already components tests, TID tests for our Hive electronics and for the individual parts for the rover electronics, but now we really want to qualify the whole system. We also have an experiment on board from a partnering university, EHA Jena, which are detecting, and also they developed a protecting circuit for single event latch ups. I have to be honest, I'm not a radiation expert. I'm more belonging to the rover team, but as you can imagine, the whole Artemis team is right now a bit stressed. I'm preparing everything for the launch, so they sent me. So don't ask me too hard questions about the radiation stuff. We also put a COTS dosimeter from Skylabs in our satellite to have a reference of the radiation environment. And which is also important, secondary mission, of course, is to get experience how the process works, because when we finally want to get to the moon, we need to understand how all that works. So let me conclude. We finally shifted our focus a bit from just building rovers into building rovers, satellites, and a whole ecosystem. We figured out that the electronics we are building for rovers is also quite handy for use in our satellites. So we are really using very similar electronics, which we hopefully can then also reuse in our rovers. So we hope, our plan is to have the same core, the Hiver, as the core of rovers, satellites, and a whole lunar ecosystem. So this is our vision. And we think Earth, orbit, and Moon only go together. You need to understand how such applications work on Moon, in orbit, on Earth, in orbit, to get to the Moon, and I would say also the other way around. So our vision then looks like having satellites with our Hiver core, communicating with rovers, doing a lot of different tasks, exploration, building up infrastructure, working together with the astronauts, and also with others. So we are really open to work with you all together to get mankind to the moon. And this is my contact. This is our website. Please check that out. We are really willing to collaborate with you. We are really open for new cool ideas, and please press thumbs for the Artemis 2 launch, because there's also a European secondary payload on it, and we'll see what we can find out. Thank you.
Thank you. Yeah. The coffee break has already officially started, but yeah, you can stay for questions if there are some. Any questions in the audience? Yeah, or does anyone have questions for the previous speakers?
Okay, thank you very much.
heritage. We have 16 missions flown, over 38 satellites of various sizes that we've helped, and all this is thanks to our facility that we have near Cape Canaveral in Florida, where we do all the preparation activities. So we do launch services and launch logistics. So the market, let's dive into it. So the market is clearly reaching an inflection point, and we can see that the number of satellite missions is rising, and obviously there is also all the services that are supported around it. And it is sort of changing in a way that there are sort of new characteristics around these services that are being conducted or executed around it. And these come based on the nature of these satellite missions. We more and more think about satellite missions as sovereign, satellites being sovereign assets in space. And we are requiring these missions being executed securely, have this ability to be responsive, reliable, redundant, and so on. Yes. So when we started thinking about logistics, it was just about these three sort of points, and we know that launch is the most difficult, or one of the most difficult parts of the journey of satellite to space. But these original pressure points that we felt there are was that there was a rising demand, like suddenly everyone wants to launch a satellite, and everyone wants it to be reliable, affordable, and there was not much more thinking around that than that. But we were battling high costs, some risks with procurement and logistics, and of course the bureaucratic and legal processes that are making all these delays and causing all these troubles for the satellite operators to prepare and execute in a way that they would like. So what happened? These original pressure points, they stayed there, but sort of the environment changed, and security became not just a checkpoint in one of the checkpoints in this mission planning, but it became a core requirement. And what has changed is that we were thinking about intellectual property, not just one part of the process, but also securing the satellite, securing all the administrative processes, securing all the procedures, accesses of people, and so on. And the other point was, well, the very sensitive geopolitical situation, market shift. So when you're building a satellite now, you can face all sorts of costs and issues that come from the fact that when you are moving satellite across borders, it can be affected by customs, and there can be some costs that you were not necessarily thinking about, and this can block the satellite on the way to the final destination of sorts, and at this point you can miss your launch slot and so on. So these two pressure points, they don't necessarily replace the original problems, but they do amplify it. So what we are looking at right now, we see that the processes, this whole supply chain is very, very fragmented. And that means that sometimes within one satellite mission, even like 10 companies can be included in the whole chain. And this becomes a problem when something goes south. That means when some problems occur, everyone is pointing fingers, but no one is taking the responsibility. It is very difficult to trace the accountability, and sort of all the launch services are provided on best effort basis and not in a systematic, thought-through way. So what there is also this problem that I've already mentioned a little bit, is these satellites being blocked at customs, missing launch slots. And another perspective is scenarios that we don't hope to happen, but these are like these unexpected emergency situations when we are in a need to move the satellite and within this, like, to have different alternative access to space, different geographical access to space, access point. And this means that we have to think about how is this actually handled? Is the satellite being handled in a clean way? What's the transport? What's the logistics? And how is the satellite secured on its way to this new access point? And what we are thinking the solution is a single entity handling all the logistics. And by that, I mean that this single entity is actually taking responsibility for everything that happens on this journey. And that also means that with this fragmentation, we are trying to standardize all these informations, have the very clear communication flow. And in that sense, being this like end-to-end solution provider. So what does end-to-end mean? End-to-end is not necessarily, okay, we are providing more and more services. It's that this one actor is responsible for the whole chain. And in Impulso, we are already addressing this by creating very integrated global logistics network and sort of taking away the headache from the customer by having this very redundant, very clear path to orbit. So we have a system, and not just like set of services, but this system that has a logic from shipment to customs, with integrated security, with all the preparation activities, storage, also hazardous tasks. And we also have this digital layer because there are always software systems included in your logistics and in your journey to space, and all the way to the afterthought of what happens at the end of life sort of situation with the satellite. So the 2 points that I would like to, or 2 concepts that I would like to talk about today is harmonization and standardization. Harmonization, we think about it as processes, and these processes, alignment of these processes. So these processes being aligned, they reduce time, cost, and risk. This means that we are creating a system that is sort of repeatable, and it is complementary. This standardization is basically complementary with this harmonization in a sense that standardization is actually the procedures. So finding common framework, finding same best practices, even the same hardware in a sense, to be able to repeat this mission execution no matter what is the geographical access point or to go to space. If it's a different timeline, different actor, different something. So we are trying to streamline it, to have it standardized. And this is not just the thought of our company, this is already happening on an institutional level. So actually the European Union is trying, I think, to also set some sort of standards for the new spaceports, so that the spaceports do take the best practices in mind from the existing spaceports, so that we can be resilient, responsive, redundant. And this brings me to interoperability. So interoperability means basically that we can change access point to space fast and safe without having to think about all these problems and issues that I've mentioned. So this means that there can be situations that happen, that occur, that previously did not happen, but nowadays they are integral part of how we plan these missions, because simply the geopolitical situation, very sensitive market changes, and so on. So, and interoperability is just a very theoretical concept if it is not translated into practice with specific actions being taken, so that this resilience can actually become practical. So what we want to do is to reduce the dependency on one single player, one specific spaceport, one specific timeline, and be able to act accordingly when there is an emergency situation, some worst case scenario basis, or any need in that sense for rerouting simply your mission to a different access point, just because we need for some reason. So interoperability as a concept with all these actionable points makes redundancy actually possible and usable. Another concept that I would like to mention is security. So when we're talking about security, we usually think about protecting physical assets. We think about protecting the satellite with its embedded data, and the knowledge and everything that's around it. But so there are multiple layers, so the physical, the digital, and the processes. So who has access? Who can get to the information flow? If there are multiple actors, how do you make sure that there is some sort of mechanism to prevent unauthorized access? And of course, the IP protection, so anything that's included within the satellite. So this digital and IP protection thing, it consists also with being resilient for cyber threats, for unauthorized access, and all of this is complemented by this another layer, which is end of life and failure handling. If you are not taking into consideration these risks, then you will even suffer some reputation damages that simply are very hard to repair at the end. We have taken this into consideration in our roadmap. We have the physical operational facility following some protocols, of course, and we have built a software layer called Nexus, where we are taking into consideration all these points that I've mentioned. I don't know if I'm running out of time, so I will try to I will speed up a little bit. But this is basically giving you the opportunity to track everything when it comes to the information flow, and that gives you better flow, better access, and a better traceability of all the information that are included, and everything becomes repeatable in a sense that you don't have to change and think about this mission by mission, but you can actually have this singular point of software layer that can work through multiple spaceports, multiple launch providers, and so on. So what we need to do, thank you. So what we need to do, we have to start thinking about mission management and this launch logistics as something that is not an afterthought, but it is embedded throughout the whole logistics chain. We have to think about it before we start planning the mission, and we have to have all these end-to-end services encompassed in it. And pretty much all these points that I've mentioned, we in Impulso, we are trying to do end-to-end services, but players or the industry, the companies in the industry can also still focus and specialize in their own best forte capabilities that they have, and then rely on partners to do the rest. And I would sort of try to wrap it up with some key takeaways. So access to space does not start at liftoff, it starts on the ground with careful planning. Resilience means being able to reroute and to change safely without with minimizing risks. And backup is not a backup if it's not usable. And security is something that should be embedded throughout the whole process. Cyber resilience is as critical as physical protection. And the clear ownership is something that helps you be aware of things that who's in charge of what, rather than adding some more checks and controls and so on. And this is the shift that's happening, and this is what we need to consider with our future missions. Thank you.
Thank you, Daniela. And at least we have time for one question, if we have that around in the audience. Questions for Daniela? I have a question, Daniela, for you. You talked about the end-to-end solution. You talk about harmonization and standardization. These two concepts, harmonization and so is very, let's say, general. And on that sense, with your knowledge, your background, your insight, what comes first, harmonization or standardization? And in what aspects do you think? Because we are talking about a long supply chain here.
I think that these are all happening in parallel, but yes, harmonization is the preparation, so these are the processes, and then we create procedures based on these repeatable processes. So it sort of comes first, but it is maybe just a help to plan for the standardization, and the standardization, and I think it must not come from like a single layer and like one single company. It has to come from multiple directions, from multiple actors. So not just one logistics company, but also the spaceports, also all the actors where it comes to storage, shipment, and all these people involved. They have to also try and strive for these repeatable procedures.
I just wish you good luck in all this, because I see the challenges with the multi-layer, multi-actor network systems, etc. So from my point of view, hopefully you survive and do a good job there. So thank you for the presentation, and let's give Daniela a big applause.
Thank you.
Next up, we have the next topic with title Economical Impact on Multi-Frequency Small Satellite Antennas, and Mayank, sorry for the pronunciation, is next up. So we give you a big applause. Meanwhile, we got the slides on.
Okay, thank you very much. Yes, so thank you very much for the opportunity and also staying for the talk. I'm a researcher here doing PhD on small satellite systems, and one of my research area is antennas for small satellite applications. But also being an entrepreneur, this is a curiosity that I had. What is the economical impacts now of multi-frequency antennas that is going to have in the future or near future space industry? So so before I start, this is a little bit sneak peek into the research that I do. I have been working on initially with patch antennas, and then now moving to very innovative projects of transparent antennas for space with solar cells integrated into it, and then also flexible meta surface antennas for very high gain performance for small satellites. I try to focus on passive antennas because this is what small satellites can afford, maybe in the future active antennas as well. And out of these high gain antennas are very, very interesting because they can enable now the market need of high data throughput satellites and also multi-frequency small satellite antennas for use cases on SATCOM as well as navigation or dual use cases as well. Taking my thought forward, why I'm even doing this and what the impact it will create has brought me into analyzing its. Of course, there is one slide about the performance, what these antennas can do about multi-frequencies, multi-beams, beam steering without requiring power. A perfect system for small satellites that doesn't need power but offers much more flexibility than normal antennas that we have seen. But moving forward, understanding what impact this would create is the topic or the focus of this talk. So what I have also observed is a lot of frequency bands are reused for same use cases across different players, and so it results into an unwanted congestion and overuse of the spectrum, which is already limited. So we need to have separate missions for separate frequencies, and then we need to optimize this spectrum usage in a way that a traditional single satellite or single band satellites, they are able to do more than, or in my words, we are able to reuse satellites as we reuse rockets. So a single satellite can do more than one objectives and may even be extended into secondary missions without requiring to deorbit them or launching new satellites. So the problem statement is the spectrum is in LEO, MEO, and in GEO orbits are getting congested, and we know about this. The bottleneck for small satellite, in addition to regulations and power requirements and other, is also in hardware scenario antennas. You can only put some antennas onto small satellites. You cannot really put multiple antennas because the volume is limited and the power is limited and the space is limited. And there is a need for a scalable multi-frequency satellite platform. And this is precisely what I worked with in my designs. And working on this, there are already multiple options that exist, which I was analyzing, which includes now so the solution that we are looking for is a low storage, high deployment, and large aperture area antenna. And what it should enable is that it is enabling multiple frequency use simultaneously without need for hardware or additional hardware. And then if we are able to reuse satellite, as I was saying, it answers a space debris problem as well. So what I analyzed is multiple different type of antennas, which is a multiband omnidirectional shared aperture, and this is like state-of-the-art technology that I was working with, and comparing the innovations and the patents that I have on these antenna concepts of deploying a flexible meta-surface antennas, which doesn't exist at the moment as a product out there for these missions. The vision is precisely this. So we will have a single satellite that can do multiple use cases simultaneously. So right now, this is the geostationary satellite case. Imagine a country that would need roughly 5 geostationary satellites to do these missions for broadcasting, weather monitoring, mobile communications, military communications. And with the technology that now I'm enabling and I'm trying to bring to the market, all of these can be done with a single satellite. So it's a cost saving of 80% right away with the geostationary satellite that I want to bring. And this is precisely what I want to come to. Analyzing the business case and the profits and the economics behind the technology, so techno-economical impact of what I was really doing in my own research. So taking the case of geostationary satellite, if you compare the traditional case with the envisioned case that I have, what we see is in the conventional multi-satellite case, we have a break-even of the investment into the space infrastructure that we do, roughly break-even in 14 years. And whereas if we have this multi-frequency, and by reducing the cost by 80%, the break-even is 2.6 years, and this is much quicker for any private player to start thinking about offering these services to countries itself. And The advantage is now low investment into space infrastructure, lesser satellites, also potentially answering to some extent the space debris problem, and then shorter break-even and profitability will enable or make it feasible for private players to start offering these multiple services that are not offered currently by other than space agencies to now bring it to the small satellite use cases as well. I also analyzed another potential business impact that this multi-frequency antennas could create, which is in MEO satellite. So in MEO satellite, the break-even also is a little bit quicker with multi-frequency satellite 2.4 years and 2.7 years. But one of the important imaginations or business propositions that I have in my mind now is with the low latency use cases, particularly now LEO PNT is coming into picture, and you have SATCOM mega constellations like Starlink, OneWeb, which are coming. So you can now design a MEO constellation that can offer multiple frequencies simultaneously, plugging in those gaps that have been left by these giants and they are not being covered by them. So offering a complementary services to Starlink or likes of OneWeb, where in this today's geopolitical scenario, not everybody wants to use everybody's service. So having a first of its kind multi-frequency constellation, and this also becomes much more feasible with the MEO because you need lesser satellites. So this is another analysis of a business proposition that I was doing, and that's basically the talk. Thank you.
Thank you, Mayank. Okay, now we have 2 minutes for questions about this very interesting topic when we're talking also about business. So I would say on the final day, final session, something that talks to me as well. So I'm glad. Thank you, Mayank. Questions? Not much questions. Yeah, one question.
So these multi-frequency antennas already exist. They are in use, but just not yet in the private sector.
Yes, so I already have designed this technology. It's part of my research, and this is what you see here. And here you see this. What I can do is multiple frequencies simultaneously, beam steering, multi-beam simultaneously, and high gain, very high gain actually. So all of these are the characteristics of an active array antennas, which are power-hungry systems, and small satellites cannot really work with them so easily. Also on multiple frequency, it's even more power-hungry and volume-intensive systems. So with my systems now, they are passive, so you don't need any more power, and this is basically my research, my PhD research now. And now we are trying to scale this hopefully this year as a startup here as it starts. But the idea is that a system that is existing and is possible under the laws of the physics, and what impact it will create now with these new cases where we are bringing satellites smaller, but then also much more powerful. So next generation of small satellites in that sense.
All right, we have one question here at the back.
Hi, thank you. Sorry, just a quick one. And what are you finding are the limitations or the trade-offs that you have to make right now, and how are you thinking of it?
Regarding the technology, you mean? Yeah. So regarding the technology at the moment, so you won't find a very large antenna small satellite system available in the market. And so I'm using membrane systems. This is where my innovation is. And now one of the challenges deployment mechanism. Because now you have to deploy a very thin sheet, and it has to be in a very perfect form that you designed it for. So this deployment mechanism is the next challenge that we are answering, and we have a couple of promising concepts that we will work with. But the idea is, if we are able to establish a deployment mechanism that gives us the perfect shape that we want and we desire, then we have essentially solved a problem of deploying a very large antenna from a small satellite without having much complex deployment mechanisms. So you can imagine a ground station in space now, and I'm talking in the size of 10 meter by 10 meter, even 40 meter by 40 meter, that kind of structures on the antenna, coming from small satellites, 30 kilogram, 40 kilogram. The gain can be humongous compared to what we have in the market today.
Right, thank you. Okay, we give the presenter an applause and we continue. And to my understanding, the next presenter is not physically in this venue, so she will present her talk, hopefully by technology, satellite technology maybe. Let's see. All right. We have Annette. We see the slides. Let's see if we also can get the presentation. At least the slides looks promising, and we can read from it that Annette is representing Haga-Helia University here in Finland.
Good afternoon. Just checking that you can hear me.
Yes.
Okay.
Can you
Good, perfect. And I guess it's now my turn to start presenting. I didn't see the stream. I'm slightly in a challenging place. I meant to be there in person today, but unfortunately I got stuck in Germany. My flight was cancelled, so I'm still in Germany. But very nice to be able to present at least this way. The presentation I prepared for this space workshop. This is actually my fourth time to be a speaker in Otaniemi for this event, so I have been one of the original ones since the beginning. And today I'm actually going to talk about, as the title says, space experience. And then it has the subtitle, A Scientific Journey to a New Frontier. So just a bit of my background. I'm actually I joined the space economy from like in a way unique angle. I'm not a scientist in a way that most of you are, that you are very technical and such, but I'm actually a tourism researcher, and I have been researching space tourism for the past 10 years. So I started my PhD 2015, and I have been writing books and journals and all kinds of things academically about space tourism. And so there's, if you want to read some of what I have written, just Google my name and you'll get quite a big list. But globally, I'm still one of the only ones, especially from the sustainable point of view. So that's something that when I did my PhD, I was actually investigating space tourism from the sustainable development angle, and that was something very unique 10 years ago, because at that time we didn't really have any tourism activity at all. Only the ones like Dennis Taito and a couple of occasional other ones who kind of trained as professionals to go to space. They were the kind of only tourists in space before 2021, when Blue Origin, Virgin Galactic and SpaceX all managed to do tourism like a related space, like jumps, basically. SpaceX did go to the orbit as well, but how we see kind of space tourism, it's more to do that you actually go, like here actually is the definition now, that space tourism, it has been actually defined in 2015, one of the first times by Duval and Hall. That was the year I started my PhD as well. So it's basically is defined as space tourism is the temporary movement of people for non-military reasons beyond the Earth's atmosphere. So that's something that it's a kind of lesser activity. You don't have to be a trained professional to go. And also it's nothing kind of military. It's just like the same as tourism activity on the soil of Earth. You go there for some kind of motivational purpose. And I'm going to actually touch that in today's presentation as well. And that's about the tourism motivations, what kind of motivation people may then have when they have a chance to go to space at some point, maybe in the future. When we think of the space tourism typology, like how it is actually classified, there are three types of space tourism. First one is the terrestrial space tourism, that you do actually from the soil of Earth. You don't go anywhere, but you do Northern Lights in Lapland. They are a good example of terrestrial space tourism. It's not really branded or marketed as, space tourism activity. It's more to do with maybe nature tourism and such. But it is actually under the category of terrestrial space tourism. That goes also for kind of space museums, stargazing trips, all kinds of whatever to do with when we are actually watching with our naked eye, for example, to space, that is already classified as a space tourism activity. And that's something kind of that is not used in the tourism industry in general at all, marketing-wise. That's something I have been promoting in my journals and also my books, that maybe even Finnish Lapland could be starting to market themselves as a space tourism destination. And that's a very sustainable form of doing space tourism, that nobody even goes anywhere. You kind of see the same Northern Lights as you do now, but it would be under the category of space tourism activity rather than doing nature-based tourism. Then you obviously have the atmospheric and low Earth orbit tourism that I just mentioned, that what Virgin Galactic and Blue Origin are now doing. Basically meaning that you go up to the Kármán line about to 100 kilometers where the space environment starts, and then you have this kind of maybe 10 minutes of like a floating experience, and then you can see the curvature of the Earth. You see how deep and dark the space is. So that's something that has been classified as like overview effect for the ones who have been going there, kind of describing that it really could touch you in a way that you really, when you see the Earth and especially the thin layer of air what we have, it is something that could be then maybe waking a lot of other people, like when they return back to Earth soil, that maybe to kind of do some environmental actions after they have really witnessed that how fragile our planet is. So that's something that I'm actually touching in my book quite a lot, but that's to kind of say that even though this is a tourism activity, but for the kind of sustainable development of the Earth and the climate change crisis, that could be a tool for some people actually, that they need to actually witness it themselves in order to act later on. Then obviously you have the Beyond the Earth astrotourism, which is the going to Mars and such, and establishing maybe colonies there. Then this is just the kind of what I just mentioned, Earth-based space tourism, that literally it combines the scientific knowledge with astronomical, cultural, natural, environmental activities. And also it could be kind of related to special interest nature-based tourism, where visitors focus especially on astronomy-related leisure or educational activities. And also the cyberspace tourism is kind of also another form of terrestrial space tourism that includes experience in such like a virtual gaming and virtual reality space travel. Then luxury tourism and customer motivation, that is something that I am teaching in Haaga-Helia at the moment, the kind of luxury tourism experience, but you think also the space tourism is part of, because it is a very elite activity at the moment. You need to have a lot of money to just to go to this kind of space jump. It is the elite form of tourism at the moment. So basically, then what I am now investigating and writing journals is kind of a multidisciplinary perspective grounded in those discourse of tourism studies, experience economy theory, and future forecasting. Also I'm actually writing another book now, and the book titles at the moment is the one that I'm presenting now, and that will be about the space experience and really kind of theoretically combining the experience economy and the tourism, the kind of side of that angle from tourism and space tourism together. So basically then in that book I am really going to these motivations of why people choose to go to experience in a space environment. So basically, what I have done, this is my last slide. Last year I created this model called Kenneth's model, which is something kind of a backbone of the book chapters I'm writing, and I have named all the chapters literally with a name of the motive tourists may have when they go to space. The first one is kairos, so it means kind of a spiritual. It's a Greek word, but it kind of highlights the fact that some people's motive may be very kind of spiritual. It's something that they are doing kind of a learning trip to themselves. And space is an environment they really need to go in order to find themselves inside. It could be something that people go to, for example, like Mount Everest trekking or something. They really want to be kind of alone with the universe. They want to have that kind of like a spiritual awakening. Then obviously extremist is something maybe like adventure seeker, like really the ones that want to really have a physical activity that nobody has done before. And kind of really put their bodies into the maximum limit they possibly can. Maybe with these kind of current space jumps, that's not something they need to really be extremist, but maybe later on if you have like a spacewalk opportunity by some company, then that is actually needed to have an adventurous mind. Then nomad would be something, a navigator, a little bit meaning the same thing, that you want to be the pioneer one. You want to be the one who tries something first. And then you literally, you are like some kind of explorer from the 500 years ago when we sailed through the world to find new continents. So it could be something similar to that. Then what I mentioned, the environmental side, the eco-explorer, something that maybe you want to be part of the nature, and this means a space environment as a nature. Then tech tourism, something you can relate maybe with, as I mentioned, cyberspace tourism, that you could maybe not to even go to space, but you could be doing some virtual avatar space trip or virtual environment space trip in the future. And then the last one is symbolist, something like maybe just to get a status to do, like a bucket list, almost like a thing in the box. And you may be an influencer or something that wants to take a selfie in space, and that would be your motive. So that's something that I just wanted to today touch with you to kind of the content of my the next book that is coming out in USA next year at some point. So thank you so much for listening, and I'm just leaving a couple of minutes for the questions, and please email me if you have any questions. So I also have the spacetourismeducation.com website that you can go and have a look what I have been writing before. But thank you so much, and if you have any questions, please ask.
Thank you, Annette. Can you hear me?
Yes.
Right, because we have a full audience here and there might be some questions for you. So I reach out to the hundreds of participants here who are listening to you. Do you have questions here? Meanwhile, the audience is thinking about a good question. Okay, here we have.
Could you elaborate on the difference between the nomad and the navigator profile?
That's something that it's very similar motivation name. That's something that's a very good question, because I may even rephrase it, but maybe it's more to do with the navigator. I'm going to write it as a metaphor to sailing. How we do, because when you think of the policies nowadays, Earth doesn't, the space environment doesn't really have it's kind of following the maritime laws in a way. We don't really have a global legislation. So I'm kind of touching maybe sailing as a metaphor. How do we do kind of exploring in international seas? What's the history of that? So maybe that's something I'm more kind of, taking as the motivational angle. And then the other one, literally nomad, could be something of it could be maybe working from space. There could be some kind of at some point we'll be in the moon, on the soil of moon. Maybe there's a hotel you're visiting, your family member who's actually working on moon, and then you are staying in this space hotel, and then you could be maybe as a nomad-wise, you could be, like as I'm speaking now to you from Düsseldorf, could be the same connection from then this space hotel. So that could be maybe what I touch in that. But I haven't really defined it as I understand what you ask, but it's still under progress. So if you have any ideas, please let me know by email. I would be happy to write.
Okay, thank you, Annette. I have a question for you, a little bit linked to this, your model, Kenneth's model. My first question is actually, is the model now based on a literature review? If that answers a yes, comes the next question. Do you have plans to validate the model with some empirical material?
The model is not based on research. It's actually a personal reason why I selected that, but that will be the backbone to do empirical research later on. So then I will be validating, I do it the other way around. So that's the story behind that name.
All right, thank you, Annette. Looking forward to read your upcoming book, and I might drop you a mail to get a dedicated copy of it.
Okay, yes.
Thank
course,
you, Annette.
I'll be happy
okay,
to.
let's give Annette a warm applause for his presentation. Thank you, Annette. And
Thank you so much.
We continue now with, I think, the last two presenters, Hannele and Minna, and we are still within tourism, space, luxury, so let's see how we will end this session. Please, Hannele and Minna, go ahead.
Oh, sorry. Yeah, I'm sure I'm going to forget to use this one. From the technology to kind of from logistics to technology to tourism, and now we're going to continue on the tourist path. So my name is Hannele Kaupinen-Räisänen and come from the University of Helsinki, and then we have Minna Pura coming from Laurea Applied Sciences. University of Applied Science, and then we also have a third author called Minna-Maarit Jaskari from the University of Vaasa. So this is an academic research we are actually doing and aiming to do an academic paper. So exploring paradoxes is the name of our the title of our ongoing research. So the background, I'm happy that I don't need to go into the tourism kind of phenomenon because we just heard about it. So that was a good introduction to that. So what we look at, it's kind of an emerging field, both when it comes to the travelers, also as a tourism kind of industry, and also an emerging field of tourism research. We can see a increasing number of research published since the first trip to space 2001 that costed about $20 million. As we just heard, it's a really small niche, and of course it's a matter of taste of what you will call that niche. But anyway, it's an ultra niche, and we are not going to go into the types of travelers that has the potential. So doing that's not in our interest at all. But of course, we could see that the travel in itself, it has the sense of luxury because it is defined by exclusivity. Just for the few, only few can pay the sum that it costs today, up to 600,000 or so. Excellency and creativity. That's what you could define it according to that. But anyways, so we have lots of research already into space tourism. but what we are looking into, when you read the research, and also when you read interviews made among those who have been as space travelers, you can see that there are lots of paradoxes and contradictions. Well, there's unique benefits and unique opportunities, and there's also potential risks and challenges. And of course, this is what kind of triggered our interest into the field. And particularly, it's inspired by the study that we did came out a few years ago. And that study, we actually interviewed people that have been to space as travelers, which was kind of a unique, because often we interview people that has the potential, you know, they kind of plan going to space or to make a trip to space, but we actually interview people that have been there. So that was the inspiration for that. And in that data set that we collected, we could see lots of contradictions, you know, potential why they wanted to travel.
Can add to that in comparison to normal motivational theories, this is a unique context. That there's always a balance of benefit and risks. That you might die, but you still want to go. So that's why we got interested into the paradoxal thinking that what's the balance, what tips the point of I want to go anyway.
Yes. So what we will take a critical look, of course, into the published studies, but also there's lots of interviews, kind of a secondary data, interviews among astronauts and also those who has traveled to space as travelers, as tourists. So we will take a critical look, and also we introduce the idea of paradoxes of space tourism, benefits and opportunities and so forth, the negative side. And then we will use the...
We take also the futurist look into the future and talk about utopias and dystopias. So utopia is the positive future, what could happen if everything goes well, what you dream of, the weightlessness, the nice experience, and the dystopia that's typically used in technology field, what could go wrong. What you typically see in sci-fi movies, there are Star Wars and everything, people die and there's lots of catastrophes. But we wanted to balance that with the positive side. What could it be and why people go there anyway?
Absolutely. And what we're going to now present is 3 of the paradoxes. Of course, remember, this is an ongoing study that we started like in the autumn. So we're going to talk about the 3 paradoxes that we have kind of detected so far. And one is the prestige seeking, also that was discussed in the previous presentation, sort of this, you know, these luxury travelers potentially, versus the altruism. So this is one quote saying that I was the first female member of the first Astronomy Society of Pakistan. After buying a ticket, I was introduced to the entire Pakistan nation of 230 million and so forth. So she was the first one to do these things. And this is something she highlighted in the interview. I talk about this, how much, because they are wonderful. But anyways, so this was kind of, she wanted to be the first, but she also talked about very much about the suit, for example, because they will get the dress, and she was something that she wanted to show off and talk about. So she had it at her home, and also the badges they got. So that was a really big thing for her. This sort of, but not the only thing. But anyway, prestige seeking. So you know, there's the status. She got a status among her, you know, the in Pakistan and so forth. So she was very motivated by self-expression and creating memorable experiences. But then we have the other side, which is also that they will want to do something for the country, the society, which she also wanted to do. She also highlighted it's not just for herself, but also that she was the first female but also the first Pakistani, and that had a great meaning for her to kind of bring the country kind of forward, and it's just not the Americans, but also we can do it in Pakistan.
So in Annette's framework, this would be the symbolist, and the other altruism could be depicted by the idea that when you go into space and see from space, look back at the Earth, and it's the blue small marble in the middle of nothing, you get the expression that, wow, I have to protect this, and get a feeling of that you need to think of sustainability and the planetary well-being, and it's deeply emotional to the people who go there. Would you like to have a fun fact about the badges that you mentioned earlier? I'm now wearing a USPA badge. What do the ones who go to space wear?
Yeah, no, well, I'm not sure if it's a fun fact, but just that it had a really important symbolic meaning for them. Those who go to space have their space suit or a badge that they have been to the space. Absolutely, and that is something particularly which she mentioned in the interviews that she kind of showed off. They had a special place at her home because it had this symbolic value. Right, and then we have this second paradox, which is exploration versus safety. And of course, you know, the paradoxes, we'll for sure going to talk about them later when we continue on the paper, but anyway, at this point. So this is an interview by another person, and she had, you know, 2014, there was an explosion. This happened 3 days before she was about to, the ship was gonna launch, and she was going, but then of course she got from the very beginning, the family didn't really much like, particularly mother, didn't like that she was gonna go, but okay, accepted it, but then happened the accident, and then she started to think more about the family, and they said that, please don't go, and then she started to think that, no, I'm not gonna go. I want to go. I'm not scared. I'm not afraid, but I don't want my parents to die of heart attack because of being so scared that I will go. So instead of being afraid really for myself, it was being scared of the family around and causing something for that. And that was also, so she actually canceled. And she got the money back, which was 250,000 euros at that, or dollars at that point. But anyway, so she got the money back, and then, but she started a foundation and all that shows she's very much into this space anyway. But yes, so here we have the human nature, of course, to explore, that also was taught in the previous presentation, to explore new frontiers.
Like the nomads, pioneers, being the first.
Yes, also related particularly to the Pakistani lady. But anyway, so what we have, some travelers are fueled by the desire to explore and discover new places. But also there's the other side, which is the safety and the sense of risk. But then again, in our interviews, none of those participated or were kind of involved in the process were afraid of their own safety. Then it became a worry about the kind of the safety or the health of those, you know, the social surrounding. Do you want to add?
That's interesting because when you think of yourself, if someone asks, would you like to go to space? Many people say, no way, it's too dangerous, I could die. Oh my God. But these people didn't think of that. They only thought about how the family is feeling. So it may be a niche people who really are not afraid of nothing.
And then we have the third paradox so far, also kind of related to all the previous ones. This is actually a Finnish guy, so he's actually Kiwi. I'm adventurous, but I don't have a death wish. Also here, I'm an adventurous guy, but you know, but I don't want to take risks, you know, because I have a family, I want to come back. But going to space is not felt to be a risk. And here is also another quote from another respondent, it's my curiosity. And if you think about being curious, that's one part of the being adventurous. That is what kind of triggers you to do adventurous things. So it's not only my love for space, it's my curiosity. Because the thing here is that, okay, so of course there's, you know, they might be triggered to participate because of gaining knowledge, to add to the science actually, but also the kind of personal adventure. But what all our interviews, if we look at what they actually share, is, as said, the fear is not there, but they all share a long-lived dream of going to space. They all wanted to see the Earth from above, and they all share the interest of sensing gravity. So these are the two things that they share. I mean, we have one guy who he waited 18 years, and during this period he became very sick, but still he went. He was 70 plus, never afraid of going. The only fear he was that he would not be able to go because he got sick, but he still went.
And I think a paradox here is that you often do research in space, but when you're traveling there as a tourist, you may become a research object yourself. So they measure your vitals and take tests, and you become the object of measuring biological changes, how you react to change, or stress, or radiation. And mentioned the SOMA, that there's open data available for scientists. It's the Space Omics and Medical Atlas. So they measure everything. So instead of doing research, you become a research object and may want to give for the society that they will learn from you something. So that's also a societal motive, that you do something for the good of all and good for the planet.
So that's where we are now. So what next? We have, of course, other paradoxes. Now we have had this very individual, micro-level paradoxes, but we're going to look also on the meso level, that is the company level, and then on the societal level. I think you already had some ideas.
Yes, so we're looking forward to discussion. What do you think are the different paradoxes? What do you think of traveling to space, but also on the organizational level, on service provider level, and on the societal level? So the service provider may think of not just the space domain, but everything, all the services that are included in the ecosystem, like booking the travel, planning, queuing for 18 years, that all entails, what kind of symbols you may wear while waiting, what the process is looking, how you enter the station, what do you do before, if it's so short period, what do you do before and after, how you get there, and how you are treated as a in the queue for the travel. And then in the societal macro level, it could mean building an ecosystem. What are the paradoxes there? Regarding safety, for example, from the service provider view, it's very important to think of safety, security, what the personnel are responsible for, how they train the people. And in the societal level, maybe how you can promote the planetary well-being, what you can do to support the whole ecosystem, that the whole ecosystem is safe and resilient. Yes.
So here, balancing benefits and risks on 3 different levels. That's what we're going to look into. And of course, there's competing values and competing priorities here in the business. But of course, we have the idea that all these would there's a need for careful consideration, also for the motivation of the travelers, also from the different layers. safety, social impact, scientific advancements, but then we have been talking about sustainability, responsibility, and all that. And of course, being business researchers, we have all these implications. So of course, we would like to highlight some responsible development of policy when it comes to space tourism.
There have been presentations today also about space law and the European space strategies, where you talk about space economy, the systemic view, and there we think that it's important to take another look at the systemic relationships and how they influence the hopes and fears and what happens in the future.
We say thank you to Hannele and Minna, and immediately we have one question here.
Just one question. Space tourism refers only to people willing to come back, or also to people maybe willing to remain to the moon or to Mars?
Yeah, if there are ones, we wouldn't know, or do we?
I think if you talk about the motivation, there are people who want to relocate to Mars, so that is a motivation. We think broadly. Moon, Mars, other asteroids, hotels in the space.
Yeah, I would say it's a good question, actually, because if they don't come back, they are not defined as tourists. So that's a good thing. Still room for at least one question, okay?
So in these interviews that you made, did you happen to see, like, could you profile people on like one side or the other, so like they're more towards this side or the other, or is something more, they're adventurous but they also have a science intent, or also, so is it more meddled than?
Yeah. Absolutely. These are not caricatures, like they are not kind of segments, but they had, I think they started with some kind of motivation, but if you wait for 18 years, if you wait for 10 years, and also, they might change. And then how we look at this space, how we define space travelers in our study, it was not about you actually launching up to this space, because the process is so long, so much happened, and they are already involved in the process from the day one they pay the sum. And that's when this space travel begins. If we look at the research on experiences, we know it's, something happens before, then we have the core experience, and something happens after. So this is a process that takes, as said, the core experience is like, 90 minutes. And we all, we just talked about, I read aloud one of the interviews saying that, you need to start to take care of your physics, because if you don't, you might go up to the space. And how many minutes are you there? For a few minutes, and you may faint. It means that you will wake up when you go down, so you will never experience the thing that you have waited for 18 years. So this is a process, and also their motivations might, differ along. They become more informed during the process.
Okay.
Wonderful question, and this is so close.
Good. All right, I think we have come to the end of this session, so I thank the audience, the presenters, and let's give the last presenter a final applause. And looking at the schedule for this workshop, we are soon at the end. There is a final words at 5 o'clock, so please attend that and see how we are closing these days here. Thank you all.